What is the reason for learning object-oriented design patterns? Learning design patterns is like learning jiu-jitsu techniques. You've probably seen self-defense or jiu-jitsu technique demonstration videos on YouTube. When you consume such contents, you can learn various methods to suppress your opponent or defend yourself by utilizing different characteristics such as human joints, the principle of the lever, and the center of gravity. As you explore various technologies that utilize the structure and mechanics of the human body, you will have realizations like, I've used it my entire life, but I had no idea I could do these things with my body. Although it's not as complex as our bodies, object-oriented programming languages offer functions that go beyond simply using classes and objects. Concepts such as inheritance, polymorphism, and encapsulation may be difficult to understand how they can be effectively used in practice on your own. Therefore, there are many people who have learned object-oriented languages like Java, but don't know how to utilize them, so they use it almost like a procedural language. Object-oriented design patterns, like the techniques created by jiu-jitsu masters through countless practical experiences and research, are systematically organized knowledge based on various problem-solving experiences stacked up by software developers. These patterns analyze real-world cases accumulated over decades to offer the most effective and validated object-oriented solutions. Through various design patterns, you can learn ways to more easily solve complex problems and make or fix programs more conveniently. Learning design patterns allows you to use the features of object-oriented languages more effectively in real situations. In other words, you'll be able to use object-oriented programming languages in a way they are intended to be used. You can write cleaner, easy to maintain code, and design more understandable structures for team collaborations. I hope this course will be truly useful and enjoyable for all those who take it. Now, let's get started with Jelko's object-oriented design patterns. In the upcoming videos, we're going to start with what object-oriented programming is and explore various concepts associated with it, as well as object-oriented design patterns. Just like you need to learn various ways of parking to learn driving and get a license. Nowadays, it's almost essential to have knowledge of object-oriented programming for programming. Programming languages of today, except for a minority like C or assembly, all include object-oriented programming concepts and features, and it has secured its place as a fundamental component of software development. Therefore, whichever modern programming language you choose, in order to learn coding, you have to climb this mountain called object-oriented programming from the start. However, for those learning programming for the first time, object-oriented programming can be an unfamiliar and difficult concept. In this video, we'll explore what object-oriented and its key components are, solely through analogy, without using any code. Those of you who are learning to code for the first time will grasp what object-oriented programming is and why it is used in programming. For those who have already learned about object-oriented programming, and for those who are going to study OODP, through the explanation in this video, it will be a time to look again, or perhaps from a new perspective, at the important components of object-oriented programming. One thing to remember is that object-oriented is a complex concept that cannot be metaphorically compared to anything in reality. Therefore, I would like to mention that what you will see in this video is just one of the many aspects of object-oriented programming. Let's think of software development as building a medieval castle. The developer is a lord who must write his instructions in documents to construct a castle. These documents of instructions are the programming codes, and the laborers to be mobilized for the construction are the resources of the computer. The programming code includes instructions on what to order the laborers to do. The most primitive method is to list each command to the laborers. Go to the forest and cut down trees. Trim the cut trees into timber. Make a beam with those timbers. Mix cement and sand. Pour water and mix it to make mortar. Stack stones in this space using the mortar. Just like this, we're giving each and every instruction one by one. These instructions will continue endlessly, and similar content will be repeated countless times. A code written in this way is very verbose and has a lot of redundancy, which is inefficient. It is also difficult to analyze and modify this afterwards. How can we improve this? First, we can group certain units of tasks together. The first 3 instructions can be bundled into make wooden component. You can bundle the next 3 instructions into lay stone. In programming, a unit that groups such repeatable tasks is called a function. Its meaning is different from the function in mathematics or functional programming, but they have a common point in that they include one or more processes. This way, the functions we've created can be reused as much as needed to write more succinct and efficient code. Now developers can command their laborers. Alright, from now on, make wood component, this time lay stone, and so on. This function is a feature available not only in object-oriented languages, but also in non-object-oriented languages like C. Up until now, we've been dealing with procedural programming. This means it's not object-oriented programming. We have improved the reusability and efficiency of our code with functions. But as the size of the software grows, this alone will not be enough to manage code complexity. This is where the concepts of object-oriented programming come into play. We are going to define roles. These roles are called classes in object-oriented programming. In the process of building a castle, such classes as the carpenter, mason, blacksmith, and engineer are mobilized. Basically, we're defining jobs. In this tutorial, we're going to call them classes and roles. Each class has its own data and functions defined for the role. This data is referred to as attributes, properties, or fields. In this video, we will call it attributes. These attributes are the state each of these laborers responsible for this role possesses. And the functions in the class are called methods. These are the actions these laborers can perform. For example, in this carpenter role, tools used by the carpenter and the blacksmith who makes those tools are attributes, and the work the carpenter does, namely make wooden component, is defined as a method. The key here is this method. Each role assigned laborer takes on the responsibility for this action. Attributes are just the data needed to perform this responsibility. Masons have the responsibility of stacking stones, blacksmiths have the responsibility of making tools, engineers have the responsibility of engineering in the form of a method called function. In this way, in object-oriented programming, before starting the construction of a castle, these roles and their respective responsibilities are first designed and defined. Then you tell the laborers, you are carpenter 1, you are carpenter 2, you are the mason, you all are blacksmiths. Like this, after assigning everyone their roles, you make them work. Imagine you're overseeing manual laborers to build a castle. Rather than just ordering them around as I initially showed, you will easily understand that this method of defining roles and assigning them to laborers is a much more systematic and manageable way. The code of object-oriented programming is usually modularized like this, separated by classes. If there's a need to modify the program, you can just find and modify the corresponding class. It also becomes possible to reuse one class in multiple programs.
So, you're saying we can use the carpenter class later in programs that build houses or bridges?
Yes, that's right. We call the laborers assigned to this role that we call a class, an instance, or an object. These objects are chunks of data that have data about the attributes and methods they are assigned according to their role. Because these data are stored in an object, people often misunderstand objects as pockets for putting data. But, as I mentioned earlier, what's important is this method, that is, responsibility. An object is a result of assigning a class or a role to certain memory resources, making it an entity with responsibility. If you haven't learned programming yet, you can stop watching the video here. Through this analogy, you should be able to grasp roughly how object-oriented programming makes a computer work and why it is a method that can make software more stable and efficient. From now on, this is for those of you who are learning object-oriented programming or a programming language that supports it, and for those who will watch the videos about object-oriented design patterns. You will be able to understand the various concepts of object-oriented programming, which were challenging to grasp more easily. Even if you don't understand what the explanation is trying to convey, please keep watching without feeling burdened. As you look at the code in the following videos, you'll easily understand what it meant. We're going to cover features common in most, but not all, object-oriented programming languages. First, let's learn about encapsulation. These classes usually do not work alone. They perform complex tasks through cooperation with other classes. For example, carpenter objects have a designated blacksmith object as an attribute in this way. They call the methods of the blacksmith object to order the tools they each use. The important thing here is that the carpenter object doesn't concern or interfere with how the blacksmith object fulfills this responsibility of forge tool. You see these plus and minus signs in front of the properties and methods. These items marked with a minus sign are private, which means they're hidden from the outside. So, objects of other classes cannot read or modify this data. This is called encapsulation. No one should interfere with what temperature of fire the blacksmith uses and which anvil he uses. The carpenter simply orders the necessary tools from the blacksmith, and the blacksmith makes and hands them over in his own way. In this way, by making sure each class is only concerned with the responsibility it's undertaken, you can reduce the complexity of the code and ensure flexibility. Typically, each class only exposes certain methods to the outside, using them as a communication interface with other classes. When writing the code for the carpenter class, developers do not need to consider how the blacksmith class is implemented. They only have to call this forge tool method, which the blacksmith has made public. And regardless of how the mechanism of the blacksmith class running forge tool changes later, it doesn't affect any other class's object calling it at all. External factors only get the output of the task through this public method. Think about how tangled and complicated the code can become when you allow classes to interfere in each other's affairs. You might guess why we encapsulate once you envisage it. Next, let's get to know about inheritance. As tasks become complex and voluminous, the types of roles required also increase. For example, in addition to creating wooden parts like ordinary carpenters, there could be a construction carpenter capable of using them to construct wooden structures. Similarly, a stone sculptor who can carve stones in addition to the work that an ordinary mason can do, and a bricklayer who stacks bricks instead of stone, these roles can be defined. Then, shall we define them as separate classes just like we defined the carpenter and the mason? We could do that, but there are two disadvantages. The first is that the code becomes verbose because there are overlapping parts. The construction carpenter class is a class that adds its own methods to the attributes and methods of the existing carpenter class, hence there is such duplicated code. It would be inefficient if we have to write these one by one every time we create a derived class, and if there are changes in the common features later, we would have to apply these one by one as well. The second is that no correlation is created among these classes with a common denominator. There are classes that share attributes and methods, but these commonalities cannot be reflected at all in programming. Here, the concept of inheritance in object-oriented programming can be very useful. A class can pass over attributes and methods to another class. When we set the construction carpenter class to extend from the carpenter class, the child class, construction carpenter, inherits the attributes and methods of the parent class, carpenter. The developer then sets this relationship and writes any additional attributes or methods that the construction carpenter class will have. This can significantly reduce the amount of code. Similarly, the mason class can have the stone sculptor and bricklayer classes derived as child classes. The stone sculptor class also has its own additional method, in addition to the attributes and methods inherited from the mason class. On the other hand, the bricklayer on the right inherits its parent's methods in a different way. The bricklayer doesn't follow the laystone method the way the parent class handed down. When an object from the mason class executes the laystone method, it simply stacks stones. However, as you can tell from the class name, when the laystone method is executed in bricklayer object, it stacks bricks. So, child classes are created to execute specific methods in a different way. Overriding the parent's method in the child's way like this is called overriding. Inheritance is not only for creating a class with added properties or methods, but also for creating a class that modifies the way specific methods operate. Of course, you can do both. The benefits of inheritance aren't just about reducing code volume through duplicate removal. It's also about being able to group different classes into one category. Construction carpenter is a type of carpenter, and a stone sculptor and a bricklayer are types of mason. This means that a construction carpenter can fit into a place where a carpenter can, and a stone sculptor, bricklayer, can fit in a place where a mason can. For example, arrays or lists that can contain mason objects can also hold objects of stone sculptor and bricklayer. In other words, a parent class can also serve as a category that groups child classes together. And this category can act as a standard that determines which classes can be used in specific positions. There are classes that solely aim to become a category. This engineer class is an abstract class. Abstract classes cannot create instances or objects by themselves. Just like there are no animals that people only call mammal or reptile. We do not assign laborers just an abstract role called engineer. It should be more specific. This class has a method called engineer, but it is only defined by its name and does not specify what it does. Hydraulic Engineer and Defense Engineer classes are child classes of this Engineer abstract class. Workers can be assigned roles as objects of these more specific child classes. They can become hydraulic engineers or defense engineers, but they cannot be just engineers. And the specification of what this engineer method does is determined in the child classes. A hydraulic engineer builds waterway facilities, and a defense engineer makes defense weapons. The role of the abstract class engineer is to act as a category that binds its children together. As I mentioned above, a hydraulic engineer or a defense engineer could fit into a position defined for engineer. Within a particular part of the program, when you write a code that instructs engineer to engineer, if you appoint a hydraulic engineer in the engineer's position, drainage will be built. And if you assign a defense engineer, defense facilities will be constructed. It's possible because the engineer's child classes must inherit and have a method called engineer. As such, another way to categorize different classes and assign the same responsibility is through an interface. In languages like Swift, it's called protocol, and there are languages like Python or Ruby that do not have this. Also remember that Go and TypeScript's interfaces are different from those in other languages. In my object-oriented videos, I will explain the interface in the way that is most commonly used, like in Java. An interface allows for different classes belonging to completely different parents to be grouped into one category. If inheritance is like receiving a family name from an ancestor, an interface is like a degree or a certificate. It can be granted regardless of lineage. Bats, flying fish, and pigeons, while each belonging to different classes like mammals, fish, and birds, all have the ability to fly. Therefore, they all implement the Flying Animals interface. The Wagon Driver interface is a certification that permits to transport materials using a wagon. You cannot create objects from the interface itself. It's like saying there's no job called Wagon Driver. All carpenters, bricklayers, and defense engineer need to transport materials with a wagon as part of their job. So, I will apply the Wagon Driver interface to these classes. It will be designated as a mandatory qualification for these jobs. Now, these four classes must implement this transport materials function in their own ways. For example, in the case of this construction carpenter, it acquires the attributes and methods inherited from the carpenter and also its own methods, along with the methods from the Wagon Driver interface. Also, they all come under a category called Wagon Driver. They can be elements in data structures made exclusively for wagon drivers, or they can be parameters in functions that take wagon drivers. In a situation where wagon drivers need to transport materials, any of these can be utilized, regardless of what type of object they are. And depending on what object is mobilized, how the transport materials is done will also vary. It's because, like the methods of an abstract class, each class that applies it implements it in its own way. In this video, we looked at various elements of object-oriented using the metaphor of castle construction. While listening to the explanation, some of you may have had various insights, and some of you may still not quite get what all this is about. Just remember the rough content for now, and as you watch the following object-oriented videos, you will be able to easily understand what the metaphors in this video are talking about. From now on, we'll explore object-oriented programming more deeply with actual programming code. I'll meet you in the next video on the topic of the solid principles. Following our last video explaining object-oriented programming with metaphors without code, in this video, we will explore the solid principles with examples of codes. Object-oriented programming is a concept that is complex to learn and utilize. Not only acquiring knowledge on the grammars and functions related to object-oriented, but there's also a lot of trial and error involved in using them effectively in the field. In sports like tennis, optimal breathing methods, hitting techniques, and movement postures are documented as regulations, which were found through the experiences and attempts of former players. When it comes to designing software with object-oriented programming, there are known 5 guidelines to make more efficient, robust, and easily maintained programs, which are known as the solid principles. The various patterns of the object-oriented that you will learn from the next video are also based on these principles. Just as there are various exceptional situations in a tennis game, although mostly adhering to these solid principles turns out to be the optimal choice, please remember in practice that there are times when flexibility needs to be demonstrated. Now let's look at each of these principles one by one. In this object-oriented design pattern series, I will draft examples using Java, a widely used programming language that includes the main syntax and features related to OOP. You can check out the sample codes on the Notion page linked in the pinned comment. If you are using other languages, you can copy the examples on the Notion page and easily translate them into your preferred language using generative AI. To follow this video, you should be familiar with object-oriented programming concepts such as classes, objects, methods, and interfaces in languages like Java. If you don't know about them, I just want to let you know in advance that it might be hard to understand the examples explained in the video. First, there is SRP, the Single Responsibility Principle. Exactly as it sounds, each class should only have one responsibility. In the previous video, we linked the classes to jobs. A carpenter works on woodworking, a mason handles stones, a blacksmith creates tools. We need to create classes to exist for one specific job.
Does each class need to have only one method?
Not exactly. Multiple methods can be used for one responsibility. However, the typical job a class carries out through these should be just one. Let's take a look at the sample code. First, here's a code that violates this principle. This user service class carries out 3 different tasks by itself. It saves a specific user's information in the database, it sends a welcome email to registered users, and even records each user's activities in a log. There are several issues with such code. First, the code of each class becomes complex, and it's difficult to intuitively understand their roles. Also, there are many reasons to modify each class, equal to the number of responsibilities it holds. A modification of one of those responsibilities could inadvertently affect the others. Because multiple responsibilities are intertwined in one place, testing and refactoring become tricky. There are also limitations in scalability and flexibility. Because these responsibilities are tied together, you can't just separate what you need and use it. Now, let's take a look at the code rewritten in compliance with SRP. As you can see, we've split the 3 responsibilities that were once packed into one user service into 3 separate classes. Just by looking at the names of the classes, you can guess what responsibilities each holds. A class responsible for storing user information, a class responsible for sending emails to users, and a class responsible for logging related to users can be easily identified. Each class only needs to modify its code when there are changes in the responsibility it has. And because classes are separated by responsibility, they are also easy to reuse as needed. In this way, the idea that each class is made with one task and purpose is the first one in the solid principles, which is the SRP. The second principle is the open-closed principle. This principle states that each class should be open for extension, but closed for modification.
The name of the principle doesn't quite connect with what it's saying. So, are you saying to extend the class rather than modifying it?
Yes, that's correct. Let's take a look at a sample code. It's a program that generates report documents as requested. The GenerateReport method of this class runs an if statement based on PDF or HTML given as an argument and generates a document in the corresponding format. In this sample code, only one line of code is written for each case like this. But in reality, very complex processes will take place here. Right now, we're only dealing with PDF and HTML formats, but what happens if we need to generate documents in other formats like XML in the future? This method will then have to be modified each time. As new cases are added, the code in this method will become more verbose and complicated. In that process, you could inadvertently affect the existing process, and there might be side effects in places where this method was already being used. Now let's look at the code applied with OCP. The function to create a document is made like this through an interface. It's an interface that defines the generate method. We don't write how the methods in an interface are performed. Just like this, methods name and form are only defined. The classes that apply this interface override this method and take responsibility to create documents in their own way. Now, if a new format is needed, you just create another class that applies this interface. In this way, you can design free from the issues that can occur during the process of modifying the existing code. The third is LSP, the Liskov substitution principle. LSP is the principle that a subclass should always be able to replace its superclass. To put it simply, a child should at least do everything the parent does. The place where the parent class object goes in should at least be able to perform the tasks the parent class used to do, even if the child class object gets put in that place. Let's take a look at this example code. In the parent class called bird, there is a method named fly. Because penguin is a subclass of the bird, it inherits this method. However, since the penguin is a bird that cannot fly, it cannot execute this method like the parent class. Fly, which works normally in the parent class, causes an exception in the subclass. Therefore, this becomes a wrong design. In such a situation, the fly method should not be a method inherited from the highest ancestor. It should be separated as an independent interface, as in the following example code. So, we are applying it only to those children of the bird class that can fly. The sparrow can fly, so it has implemented this interface, and you can see it's not applied to the penguin. So, there is no LSP violation in this code. Let's look at another example of violating LSP. This rectangle class has width and height properties, and it has setter methods to set these values. And this square class inherits from the rectangle class. Because a square is a kind of rectangle in geometry, this inheritance structure seems appropriate. The square class's setter methods for width and height don't take away functionality from the parent's methods, but instead add functionality like adjusting its height to match the width, so it seems like there won't be any problems. However, from a broader perspective, the square class does not have the functionality to specify different widths and heights, unlike the rectangle class. In the square class, when you modify the width, the height also gets modified, and vice versa. For example, if the width and height of a rectangle are set to 5 and 4 respectively, and the area is calculated, the output will be 20, but if you replace it with a square, the width set to 5 becomes meaningless, and 16 will be output.
So it's not just a matter of overriding methods.
Yes. Therefore, if you want to design such programs based on LSP, it would be desirable to remove the parent-child relationship between rectangles and squares, and make them separate classes applying the interface called shape. Now that the rectangle and square are separate classes implementing the shape interface, there's no problem. The fourth principle is the ISP, the Interface Segregation Principle. This principle is simple. It states that a class shouldn't be forced to implement methods it doesn't use. In the last lecture, we said that an interface is like a certification. If you had to know how to operate not only a regular car but also an excavator to get a driver's license, most people who get their driver's license would have to learn how to operate an excavator they will never use in their lifetime. Just as there are separate licenses for cars and excavators, interfaces should also be separated according to their responsibilities. Let's take a look at an example. This worker interface, designed to be implemented by factory workers, has work and eat methods. A class that implements this interface must implement these two methods. A regular human employee wouldn't have an issue performing both methods, but a robot does not eat. Therefore, if we introduce robot workers, this eat method would become redundant. Hence, we can separate this interface into workable and eatable, and allow regular employees to implement both, while robot workers only implement workable. Now, as long as the robotic employees only implement work of the workable interface, they don't violate the ISP. Lastly, we have DIP, the Dependency Inversion Principle. DIP is a principle that high-level modules should not depend on low-level modules, which might be hard to understand. Let's take a look at an example code. We have a fan class and a switch class. The switch class contains an instance of the fan class as an attribute, and when the methods to turn the switch on and off are executed, the fan operates and stops. Here, since the fan implements the specific action directly, it's a low-level module, and the switch provides abstracted logic to control this, making it a high-level module. However, in this code, the high-level module, the switch, is dependent on the low-level module, the fan. This is because the codes of the fan class, including the spin, stop methods, are being used as they are inside the switch class. If the names or parameters of these methods are changed, the run part of the switch class must be modified accordingly. Also, in such a structure, a switch can't handle other electrical appliances besides the fan. Therefore, in the modified code, we create a separate interface called switchable that has turn on and off methods. And the fan implements this interface, becoming part of the switchable category. Then, the switch treats the objects of the classes belonging to switchable as properties and executes their turn on, turn off methods internally. The switch and the fan do not communicate directly, but communicate through this switchable interface. Now, Any modifications to the fan's methods will not affect the switch class, and a switch can handle not only a fan, but also any other classes that implement switchable. With this, we have now covered all the solid principles. Each principle speaks to different aspects, but I believe you would have easily grasped what they collectively pursue. Remembering what you have learned in this video will assist you in understanding the object-oriented design patterns that you will learn later on. Starting with the next video, we will explore each of the major design patterns of object-oriented programming. Let's start reviewing the patterns of OODP now. If you connect to yalco.io, you can see this Notion page. Click on Object-Oriented Design Patterns in the Yalco Lectures section. And if you click on OODP Example Codes and Materials, you can view a list of the patterns we will cover, and by clicking on each, you can check the example codes used in the lectures. The example codes are all written in Java. This lecture assumes that you can understand code written in Java or similar programming languages like C# without any significant difficulty. If you are not familiar with object-oriented concepts and syntax such as classes, objects, static, and instance, abstract classes, and interfaces, I recommend that you get at least a brief understanding of these first. This list in the page categorizes the patterns by their type. However, in this course, we're going to study the patterns in a different order. In order to lower the entry barrier, I've planned to start from the easiest patterns, and to prevent boredom, we're going to cycle through different types of patterns. So, let's start with our first pattern, the Facade Pattern. The Facade Pattern is one of the easiest to understand, allowing you to implement it even if you don't know the syntax of an interface. Facade is a French term that refers to the exterior of a building. This pattern is similar to a drive-through service at a fast food restaurant. On the building's exterior, there's a window that takes orders and dispenses food. Inside the building, there are various areas for different purposes, such as a cash register, a cooking area, a drink machine, a wrapping station, but customers don't need to know about this internal structure as they receive all services through this window. Thus, the Facade Pattern is a pattern that makes it possible to use a complex system made up of multiple elements simply through a single interface. The code written in the Facade Pattern consists of a subsystem made up of multiple classes, a class that plays the role of facade, integrating these and providing a single window, and a client that uses functions through this facade. Now let's look at the first example. There are electronic devices such as a thermostat, lights, and a coffee maker in a house. In this way, each device is made as a class. The thermostat has the function of setting the house to a specific temperature. The light has the function of turning it on and off. The coffee maker has a method set up to brew coffee. When the owner of this house wakes up, they set the temperature, turn on the lights, and brew coffee. That means they have to manually operate each of these devices. Isn't there a way to have all of these actions performed by pressing just one button? The homeowner purchases a smart home system. This Smart Home Facade class plays the role of the facade in this example. All the appliances I just talked about are connected to this smart home system. Like this, the objects of the classes created for each device are held as fields in this facade. In this way, each was brought in as a constructor and put into the corresponding field as a value. This system has two buttons on the wall that execute such methods. When you press the button that executes the wake up method, it sends commands to the connected devices to set the room temperature to 22 degrees, turn on the lights, and brew coffee. When you leave the house, you can press the Leave Home button to set the temperature to 18 degrees and turn off lights. Shall we take a look at the code of the main method, the execution part? In this lecture, we will call the class with a main method that runs the entire code as client. After creating objects of the temperature control device, lights, and coffee machine like this, and putting them as arguments in the constructor and creating an object of the smart home system, now you can simply issue commands through this facade called smart home. You can see these results in the code that presses the wake up button, and these results are output in the code that presses the leave button.
It's truly a simple pattern. It seems like a structure that people are already using a lot, even without learning it as a pattern.
That's right. This is also why we first dealt with this pattern. With the use of this facade, the client writing this main method doesn't need to know the details of the internal implementation of each of these subsystem classes, and can perform all the necessary functions through the integrated and simple interface of the facade. Even if the usage of the subsystem changes, you only need to modify the facade's code, not the client code. Thus, the flexibility of design is also improved. We will look at the second example now. There's a class for reading files, a class for writing files, and a class for deleting files. According to the first principle of Solid, we created classes for each responsibility. However, it can be quite cumbersome for the client to individually create and handle each of these three. We write the facade that combines all three into one class like this. This file system facade also has instances of the three classes we just saw as fields, but you can see that they aren't coming from outside, but are each directly created in the constructor like this.
So the facade takes care of creating the subsystem too.
Yes, and it has these three methods, each representing their functions. The method to read files executes the method of same name in the file reader. Similarly, you can see that the methods to write files and delete files execute the subsystem's methods. Shall we take a look at the code of the main class, which is the client now? As you can see, all you need to do is create and use this facade class object here. You can see that the classes of the subsystem are not used at all in this code. This facade class handles even the creation of subsystems objects internally. So with just this facade's object, you can issue all commands to create, write, and delete a file. You can use each function by calling the methods of the facade object like this. In this way, we examined the facade as the first pattern of OODP. It would have been a simple and easy pattern without any difficulty in understanding. I will see you with another pattern in the next video. The second pattern we're going to look into is the strategy pattern. This pattern sets up several methods or strategies for performing a particular task and allows them to be interchanged as needed. In other words, think of it as creating various modes of performing a task, each as a class, and selecting and using them as needed. Shopping carts are lined up in front of the cashier of a large supermarket. When it's their turn, all these carts perform a function called checkout. But there can be several ways to perform this function. You can pay cash, you can use a card, or you can pay through PayPal. All of these options are the modes and strategies for this method called checkout. Each of them becomes the specific algorithm of this checkout method. Now let's take a look at some code written to implement this. We first create an interface called Payment Strategy. As the name suggests, it's a strategy for making a payment. As you may already know, an interface just declares the names and types of methods. It does not write any implementations. The methods defined in the interface are implemented in the applicable classes. Here are two classes that implement the interface: credit card payment and PayPal payment. Applying the payment strategy interface signifies two main points. First, these two classes belong in the category named payment strategy. And second, they both need to implement the pay method of payment strategy in their own unique way. These classes, despite having a different number of fields and constructors, their objects can all take the place of payment strategy and are used for the purpose of running the pay method in that position. Next, let's take a look at shopping cart class. This class has the payment strategy interface as a field. So this is where one of the two classes that apply the interface could be fit in. And to allow for replacement with other strategies at any time, there is also a setter method like this. Also, when executing the checkout method of this class, it runs the pay method of the currently mounted strategy object.
The strategy could be thought of as different types of bullets, such as live rounds, paint bullets, rubber bullets, and this context is the gun.
Yes, it's one way to look at it. Then, this setter would be a method for loading bullets. Now, let's take a look at the main class which handles this gun. Firstly, create an object of the shopping cart gun like this. Then, use this setter method to set the strategy, that is, load the bullet. We first create an object of credit card payment and add it. The first calculation is done with a card. When you fire the gun named shopping cart with the selected strategy using the checkout method, the pay method implemented in the credit card payment class is executed, and this string is printed out. Let's modify the strategy this time. It's like loading a different bullet. You can create an object of PayPal payment like this in the same object, and if you run the checkout method again, you can see that it produces a result like this. This pattern separates several algorithms that perform specific functions into individual capsules, thus allowing them to be switched out at any point during code execution. If a new method needs to be added, you can easily extend by creating another strategy class, and it also becomes possible to reuse them in other places.
So, whenever something changes, I just need to modify the corresponding strategy, and if a different method is needed, I just make a new strategy. This would be code that adheres to the open-closed principle we learned from Solid.
You're exactly right. Now let's move on to the next example. The structure is exactly the same, it's just the content that's different, so let's take a quick look. It's a program that transforms a given string into another string using a specific algorithm. So in this interface, the compress method is declared, which takes a string as a parameter and returns a string. These two classes implement this method in different ways. The compress of the first class records the number of times each character in the string is contiguous and compresses it, while the compress of the second class transforms each vowel of the string into a predetermined number. The next class, compressor, is a context that fires their objects. Just like the shopping cart that we saw earlier, there's a field where strategy class objects go in, a setter that sets its value, and a compress method that executes the compress method of a strategy class object. Finally, this is the code for the client executing it. Here, this string will be transformed using the two strategies we've just examined. If you use the first strategy, run length encoding, you will get such a result, and if you use the next strategy, simple replacement compression, you can see this string being returned. You will easily understand if you look into the methods of these strategy classes in detail, each of which represents an algorithm. In this way, we've taken a look at the strategy pattern. If the concept of interfaces wasn't new to you, there wouldn't have been any difficult parts in this pattern. In the next lesson, we will get to know the template method pattern. The pattern we are going to discuss in this video is the template method pattern. This pattern is used when you need to implement tasks that need to be executed through certain predetermined steps. This pattern is useful when we need to ensure that the whole process is executed in a specific order, although we can implement how we perform each step in various ways. Think about dining at a French restaurant. A typical French meal consists of these courses. If it's the high-end restaurants that value tradition, they would serve food in this particular order. There can be various food items served in each stage. For the hors d'oeuvre, a salad, smoked salmon, or snail dishes could be served. For dessert, tarte, crème brûlée, or macaron could be served. Depending on what menu is chosen for each stage, you can have numerous combinations, but to be recognized as a traditional French restaurant, you must adhere to this order defined as an abstract class. This is the template you have to follow. Now, let's look at some examples. Assume there's a process of making hot beverages like coffee or tea. We'll assume that whatever the drink is, it goes through a common process of boiling water, brewing the drink, pouring it into a cup, and adding condiments. For this, we'll create an abstract class like this, while an interface allows you to only declare each method without implementation. An abstract class allows you to write the implementation of the methods you want. A method for boiling water, a method for brewing the drink, a method for pouring the drink into a cup, and a method for adding condiments are either just declared or fully implemented like this. The reason why we need to use an abstract class instead of an interface is this prepare recipe method. This method must have an implementation like this. This method acts as the template method in this program. Here, you can see that the mentioned methods are being called in this order. So, this becomes the template of this program. Shall we now look at the classes that have actualized this? There are the tea class and the coffee class. Only the brew method and add condiments method, which are not implemented in the beverage class, are implemented here in their own ways. Regardless of how these classes implement their respective methods, the brew method comes after the boil water method, and the add condiments method comes after the pour in cup method. Shall we take a look at the client code lastly? I told you, abstract classes and interfaces become categories for classes that extend or apply this. So, you can put tea and coffee objects in a variable of beverage type like this. Firstly, let's try to invoke the prepare recipe method from a tea object. As you can easily predict, these methods are invoked in order, and you can see that such a result is output. It's the same even if you run it with a coffee object. Thus, the template method pattern can be useful in cases where the structure of the algorithm to be implemented is fixed, but each detailed process can be changed or expanded. Let's take a look at a more practical example this time. It's a program that reads files of various formats such as JSON, XML, CSV, processes them, and then saves them in other forms. Like this, you load the file, check if the file is written in the correct format, process it according to a predetermined algorithm, and then save it as a new file.
So, this process method is the template. Here, instead of just executing these in order, it uses a conditional statement based on one of them.
Yes, the template method can be used in this form. After loading the file, depending on the execution result of the method that checks if the file format is correct, it either executes the remaining two methods or produces an error message. Now, these are the two classes that inherit from this abstract class. Each of them implements the process of handling CSV data and JSON data respectively. The validity of data is determined by whether the given string as a parameter includes CSV and JSON respectively. The remaining part is just code that prints out the process, so pause the video and take a look at the code if needed. It shouldn't be hard to imagine how this code is used by the client and how the results come out. Like this, you create instances of these two concrete classes and you run them by calling the template method named process. If the data you input matches the format represented by the object, all the processes are run and such a result is output. In this way, when you put XML data into a JSON data processor, you can see that this message is displayed. Thus, we have examined the template method pattern. If you keep this pattern in mind, you will have times when you find places where it can be useful in the field. In the next video, we will look at the very famous and also useful pattern, Singleton. In this video, we are going to delve into the Singleton pattern. Singleton is one of the particularly unique and important patterns in OODP. This pattern is necessary when in a program, a particular class's object should be created only once. To understand this pattern, you need to know about static members. Elements of a class, namely fields and methods, consist of instance elements and static elements. Instance elements are created with each new instance, that is, an object of the class, and they take up memory space. However, static elements are created only once, regardless of the number of created objects. Let's assume there's a hamburger chain called Jalkoburger. We can define a class representing Jalkoburger like this, and we can create instances, in other words, objects of them. A class can be compared to the chain itself, and each object can be likened to the stores located here and there. Among the fields this Jalkoburger class has, the ones without the static are instance fields, which are data belonging to each object, that is, store. Store location, manager's name, and the presence of a drive-thru are data that should exist in each store. They must be created as many as the number of objects and stored in memory. On the other hand, static elements are part of the chain Jalkoburger itself. They're not data belonging to a particular store, which is why only one of them is needed, like the brand name and the CEO's name. Since this isn't a programming language class, I'll stop explaining about static here. Now, let's look at why this concept of static is needed in Singleton Pattern. Sometimes you need a type of data that can exist in only one instance in a program. For example, like the dark mode status in a program that provides UI. This data should be applied uniformly throughout the program, so it becomes problematic if it's stored in more than two places, because buttons could be in dark mode while text fields remain in white mode. Different theme modes should not coexist within a single screen. Therefore, a static boolean named isDarkMode like this would suffice for such a purpose. And if other fields and methods need to be included in this theme settings, you can define a class like this and then its object. The problem is that an object of a class can be created as many times as you want unless you take any measures. We need to make sure that this theme class object is never created more than once in the program. The technique used for this is called Singleton. Now, let's look at an example applying the Singleton pattern. Interestingly, in this theme class, a private access modifier is attached to this constructor. This is to completely prevent the use of this method outside of this class code. It's as if the chain has blocked off chain applications. From the outside, you absolutely can't create an instance, an object of this class. Because you can't use its constructor, then how do we create and use an object of the theme class? First, let's look at this field called instance. As you can see, it's a static field that can only exist one in the program, and its data type is the class itself, the theme. The only object of the theme class is stored right here. It's like having the only store of the chain housed in the chain's headquarters, and the code that creates this object is in this method called getInstance. Since it's a static method, it is called not from an instance, but from the class itself, and this method is the key part in Singleton Pattern. Firstly, this method checks if this instance static field is null. It should be null at the first execution, because no value has been assigned yet. If it is, it creates an instance of this theme class itself through the constructor and assigns it to the field. It's possible since even a constructor with private access can be used within this class. Normally, we need to add some synchronizing related codes for multi-threading environment, but since this is not a Java tutorial, I'll stop here. After this getInstance method is called once, this instance field will no longer be null, so this part will not run anymore. This method returns the instance field, which is created and assigned only once, like this. Because the constructor is written like this, the initial value of the theme color field will be light. Later, this setThemeColor setter method is used to change the value. So it's a method that changes the theme color field of a theme instance, which exists uniquely on the program. On the contrary, this getThemeColor method is a getter to access that value. Now here's the code for the classes that require this theme color. UI elements like buttons, text fields, and labels are each made into classes. The part to pay particular attention to is this code. Please pause the video for a moment and focus on this section of the code. When you run the display method, which means to render each element on the screen, it fetches the color specified in the current theme settings like this. As we designed it, this theme class is a singleton, so it accesses the unique instance via getInstance, a static method, and uses this getter to get the value of the theme color field. The rest of the code parts are not so crucial in this example. Now, let's examine the client code. The button, text field, label classes we just saw are not singletons, so they're created using a constructor like this. And then we execute each display method like this. This is the very method that uses the value of the singleton class we just looked over in the previous code. As a result of executing this method, you can see such a result appearing. The light value retrieved from the singleton object, which we just looked at specifically in these parts. It appears as a result like this. It's not confirmed at this point, but we can infer that all these values came from a single object. Now, let's verify this. In this client code, we access the only object of the theme class using the getInstance method, and then we change the value of theme color to dark using the setter method this time. After that, if you run the display method on the objects of the button, input field, and label again, you can see that results like these are output. In this segment, the value light was embedded in all the strings, but as you can see, after modifying the field value of the singleton object, all of them were output as dark. This implies the theme class objects referred to in this segment are all the same, a single instance. At this point in the client code, where the display method is first called through the object of button. In other words, when the getInstance method of the theme class was first called right in this method, the creation of the singleton object occurred only once, and since then, that unique object has been continuously returned and used. If you look carefully at the sample codes on the Notion page again, you should be able to understand it without difficulty. Now, by utilizing this singleton class, we can prevent the issues that arise when more than two instances of any class exist. If you're using a different language, you can translate this code with an AI tool to examine it. This singleton may be written in many different ways due to differences in syntax among languages. But if you remember the principles and key points we learned in this video, you can easily understand code in other languages. In the next video, we will explore the state pattern. The pattern we are going to learn this time is the state pattern. In this pattern, a state of something exists as an object of its corresponding class. For example, with a door, open state and closed state each exist as a class. The door has the function to open and close, and the execution result of these functions changes depending on the current state of the door. Let's go straight into the example code. There is an interface named state like this. There are declared methods for opening and closing the door. Now let's create a closed state class and open state class that apply these interfaces. Each represents the state of the door being closed and opened respectively. You can also see that the open and close methods defined in the interface are implemented differently like this. In other words, the way to execute given methods is differently implemented for each state. There's another class called door. As you can see, it has an instance of the state interface as a field. So this state, like closed or open, is contained as the attribute of this door. Initially, the closed is initialized. It starts with the door being closed. What happens if you give the close command in this state? Since the door is closed, the close method of closed state is executed. This method only prints a message that the door is already closed and ends. So, how about we execute the open method? Execute the setState method of door by creating and inputting an instance of openState as an argument. That is, it's about changing the status of the door to open. Now, when the open and close methods are executed in door, what is implemented in the openState object is executed. If you try to open the door again in this state, a message that the door is already open is printed out. And if you give an order to close the door, it changes the status back to closed. Whenever you transition from one state to another, you can see that a new object of the target state is created and put in with the constructor. When transitioning from an open state to a closed state, you create an object of closed. And when transitioning from a closed state to an open state, you create an object of open and put it in door.
If I didn't use this pattern, I would have had to implement it with an if statement for each state, right?
Yes, that's right. As the states diversified, the conditional statements would have become much more complex. Now, when the client code creates an object of the door and executes the open and close methods, the result that will appear is not difficult to predict. The status of the door is initialized to closed at the point of creation, and it's not hard to understand that it transitions to the open state at this point, and then returns to the closed state from here. And the messages from open and close methods are printed like this, according to each state. Like this, the state pattern separates something's state into classes for each value. Each of these states implements methods in their own ways, and when necessary, they change themselves into different states, reducing code complexity and increasing flexibility. Now, let's take a look at the second example. It's a program that describes the operation of a video player with the state pattern. The state interface in this example has play and stop methods, and the three states of stop, playing, and pause are each defined as separate classes. You can think of it as toggling back and forth between these three states with a remote control that only has a stop and play button. The video player class that uses these states has the same structure as the door class in the previous example. Therefore, I won't explain this code separately. Now let's take a look at how play and stop work in these three states. First, the stop button in the stop state does nothing. You can see that it just outputs a message saying it's already stopped. When you press the play button, it switches the state to playing. From that point on, the methods of playing state are to be executed. You can also see here that we're creating and using an object in the playing state. As you might expect, the play button in the playing state does nothing. And if you press the stop button while playing, it will initially go into this paused state. In the paused state, both buttons perform meaningful actions. If you press the play button, it will be back to the playing state. On the other hand, if you press stop once more, it will move to a completely stopped state. The client code is also like the door example we saw earlier. As written in the constructor of video player, the initial state is stopped. When you press the play button, it immediately goes into playing state. If you press stop, it becomes paused. If you press the play button again to return to the playing state and press stop once, it becomes paused. And if you press stop again, it fully stops. If you did not use the state pattern and wrote the code with conditions, it would have looked like this.
The total code length has been reduced, but as the states and conditions get complicated, this part also becomes complicated to write, and it seems like there will be more room for mistakes.
You're right. You need to remember that short code is not always good code. By using this state pattern, we can flexibly manage actions depending on the changes in object state, and you will be able to write readable code without complex conditional statements. Next time, we'll take a look at the adapter pattern. The sixth pattern we'll look into is the adapter pattern. Each country has a defined standard of the shape for electrical plugs. For example, the shapes of plugs in the United States and France are different like this. If you want to use a MacBook charger that you used in the United States on a trip to France, what should you do?
Us bunnies, we cut off the wire with our front teeth and replace it to fit the French standard.
That could solve the problem, but it would ruin a perfectly good charger. With an adapter like this, you can use your existing product in a country with a different standard without having to modify it. In the adapter pattern we're going to learn today, there is a class that plays this adapter role. Let's jump right into an example. Here we have two interfaces. Old message sender is an old interface used in the early days of a program. Modern message sender is a more modern interface that is used today. As you can see, the names of the methods, parameters, and return values are all different. It's like the plug-in standards in the US and France have different hole shapes. Now we will examine this old message system class. This class applies an old standard, the old message sender interface. So it's a class created during the initial stage when this interface was used. It's like the MacBook charger used in America. Therefore, it has pins that fit into the hole of the American standard. It can't be used in France, where the standard is different. If we modify this class, we would need to modify all existing codes where this object is used. So, how can we use this old style class where modern standards are needed? Like the plug of a charger, we can create and use an adapter like this. This message adapter implements the modern message sender interface. In other words, it's an adapter with pins to fit the French standard. In doing so, it has a field object of a class that applies old message sender. That means it has a hole where you can plug in an appliance of American standard. The objects of old message system are American chargers that belong to the type old message sender, so they can be plugged in here. Like this, the constructor receives the American charger as an argument and stores it in the relevant field. And in this part, the American input is converted into French output. It will call the sender method, which is implemented as defined in old message sender. This is done using the send message method as defined in modern message sender. If you pause the video and take a closer look at the code for a moment, you'll quickly understand the principle. The way they're used in the client code is simple. First, you create an object of the American charger, then create an object of the adapter, and plug in the object of the American charger. And when you plug this into a French power outlet, you can confirm like this that it charges properly. So, if you want to put an object of a class that was written before in a place where only objects of modern message sender can go, you can use it like this by plugging it into an adapter class. Now let's look at another example where an adapter is used. There are three classes, namely USB, HDMI, and VGA. Each has its own method for connecting the cable with different names and parameters. Therefore, they cannot be grouped into a single category for uniform use, because each requires a different way of calling. It would be more convenient if we could call all of them through one method defined in this display adapter interface. To do this, we create each of these adapters like this. As you can see, they all implement the display adapter interface. Essentially, it's an adapter that allows you to plug USB, HDMI, VGA into a plugin called display. Therefore, all of them execute the function through the display method. And inside those methods, the methods of the USB, HDMI, VGA objects that are fields in the corresponding adapter are executed. Now, let's take a look at the client code. First, create objects of USB, HDMI, and VGA that are not connected to the adapter. These are objects of unrelated classes, so they cannot be contained in one array or list. Let's have a look at this array list. This list can contain objects of type display adapter, the interface we just examined, and these adapter classes are all classes that implement the interface. Therefore, objects of these classes can all be contained in that list. We're returning to the client code. Like I said, all of these three adapter classes can go into this list like this. And in these adapters, objects of USB, HDMI, and VGA are contained as fields respectively. That is, through the adapter, unrelated classes can be included in one list. And this way, it is operated by a for loop, and it can be uniformly run via the display method. As a result, you can confirm that a text like this is output. Like this, the adapter pattern is a pattern that allows classes with incompatible standards to be used in the same way in one place without modifying each code, using an adapter to connect them. Through this, you can pull in and use old classes with different standards, or you can bundle different classes together and use them in bulk with a single command. Next time, we will learn about the bridge pattern. The pattern we will learn this time is the bridge pattern. The bridge pattern is a way to separate abstraction and implementation so that they can be diversified independently.
I don't quite get it. What does it mean to separate abstraction and implementation?
Let's take the example of a TV and a remote control. They both have power and volume buttons. If you press the TV buttons, the TV itself performs the corresponding functions. That is, the TV is implemented to how to turn the power on and off and adjust the volume. So here, the TV corresponds to implementation. On the other hand, the remote control buttons just send the corresponding commands to the TV. That is, on the remote control, only what it can do is defined. So this remote control corresponds to abstraction. The TV doesn't need to know about the existence of the remote control, but the remote control needs to know what device it targets. So the class of abstraction depends on the class of implementation. Before we go into the code of the first example, let's look at the diagram first. In the bridge pattern, the abstraction part and the implementation part are each separately written as an abstract class and an interface. And between the two, there's a bridge set up by the abstraction part referring to the implementation part. Since they are separately written like this, each can be diversified into different classes like this. So, like this, you can control the TV with a basic remote, and you can control the radio with a high-end remote.
So it's like if we separate the topping menu and crust menu for pizzas, we can make a lot more diverse combinations, right?
I suppose you could think of it that way. Now, let's take a look at the sample code. We'll start with the section that corresponds to the device in this implementation. The device is written like this as an interface. As you can see, the functions of turning on, turning off, setting the volume, and checking the active status are written as methods. Because the device is an interface, the methods are only declared like this here. Let's move on to the next classes. Here are the TV class and radio class that apply this interface. The methods declared from the device interface are implemented like this. You don't need to take a close look at the details. We've viewed the codes of these implementation parts with that. Now let's look at the codes of abstraction parts. I guess we have to check the code of this remote first. The remote is written as an abstract class like this, because it needs a field. You can see that the instance of the device interface we wrote earlier is stored in the field via the constructor like this. That is, the remote is dependent on the device. This dependency relationship works as a bridge between abstraction and implementation. The rest of the parts are written as abstract or concrete methods, which are the functions of the remote control. And from this, we have the basic remote control class and the advanced remote control class that were inherited. The code is something you can easily grasp just by giving it a quick look. Overall, it's a code calling the methods of the device that the class depends on, such as TV or radio. The difference is that an advanced remote has these additional methods. Now, let's take a look at the client code. First, create instances for the implementing classes, TV and radio. Then, when creating instances for the basic remote and advanced remote, set the TV and radio objects as the receivers. Lastly, by invoking various commands through these remotes, you will be able to see a result like this. Just like this, because the remote part and the electronic device part are divided, yet connected through a bridge. Even if there are changes in the remote part, it does not affect the TV or radio. And with the electronic device part as well, you can create the necessary derived classes regardless of what kind of remotes there are. Now, let's move on to an example that's closer to real-world practice. The second example involves the process of sending a message to a recipient, which is divided into this implementation part and this abstraction part. First, the implementation is based on an interface called message sender. And then there are classes called email sender and SMS sender that apply this. The only difference between the two is the message they output. Anyway, they are the ones who directly send the messages, so they belong to the implementation part. Let's look at the abstraction part now. This way, there is an abstract class called message, and there are derived text message class and encrypted message class. By having an object of message sender as a field, it bridges the implementation part. The difference between a text message and an encrypted message is that while a text message sends the message as it is, an encrypted message adds the process of encrypting the message. The client code part is the same as the first example, so there's no need for me to explain it additionally. You can see the code for sending a text message via email and its result, and the code to send an encrypted message via SMS and its outcome like this. In this way, we've seen how the bridge pattern can be used to divide one process into two divisible parts. Next time, we'll take a look at the factory method pattern. Our eighth pattern is the factory method pattern. This pattern may have a simple structure, but its application can be difficult to understand. So I prepared 3 examples for this video where you can see different uses of this pattern. Let's first examine the structure of the factory method pattern. In programs written in object-oriented languages, classes are used. The objects of these classes are created and used in specific contexts, like client code. In the case of this diagram, the class is directly connected to the client, and the client runs the constructor. The factory method pattern involves placing an intermediary, a factory, between the class and the client. Now, the client code is connected not to the class that makes the instance, but to the factory. The factory is delegated to create instances of the class and, if needed, process them in a specific way. Let's take a look at the sample code right away. First, there is an interface called vehicle, and there are car and motorcycle classes that implement this. These are classes intended to be made into instances for use. Typically, in client-side, the constructors of these classes will be called directly to make the instances. But in factory method pattern, we separately create factory classes for vehicle, car, and motorcycle. This is the code for those factories. First, an abstract class that creates a vehicle object, which is an interface. Just like this, it's directly connected to a vehicle by having an instance of vehicle as a field. And there are factory classes for car and motorcycle that inherit from this abstract class. In the createVehicle method, overridden from their parent class, you can see that they run the constructors of car and motorcycle, respectively, to create instances. Let's take a final look at this deliverVehicle method. Here, instances of car or motorcycle are created and stored as implemented by the child classes. And in the case of this example, this method also proceeds to call the methods of the corresponding instances. Now, let's look at the client code. As you can see, car and motorcycle classes are not directly utilized here. You can see that only their factory classes are created and used like this. And when they run the deliverVehicle method that they commonly override, you can see the results of running the drive methods of the car and motorcycle classes like this.
I see that car and motorcycle have been separated from the client, but I still don't quite grasp the practical use of this pattern.
Yes, so let's look at the next 2 examples where this pattern can be useful. In such a case, without using the factory method pattern, if the class is directly connected to the client and another class of the same kind is created, changes reflecting this would need to be made on the client as well. If we create a factory that handles the management and creation of these classes and put it in the middle, the client code won't have to worry about changes in the detailed types of classes. In the second example, we have an interface called product and the classes electronics, clothing, and book that apply this. Their create method is simply a method that outputs a message. Next are the classes of factories. First, there is an abstract class, product factory, and on the right are the concrete factory classes derived from it. Depending on the need, other factory classes can also be created. In this example, this single factory creates instances of 3 classes. Depending on the argument given to the create product method, an object of electronics, clothing, or books is created. One of the instances created like this is returned by the order product method. The client code looks like this. As you can see, only this factory class here has the constructor being called. And depending on what string value you put in order product, it is determined which class object will be returned. You would have been able to easily predict what the result will be. In this way, by completely delegating to the factory which class objects will be created and used, the client code can be separated as an independent element that is not affected by changes in the type of product. Now, let's look at our last example. In this example, there is a factory for each class, as in the first example. The same pattern can be implemented in various ways depending on the needs. The purpose of this example is to ensure that when the constructor of a class changes, it doesn't affect clients, but the factory is modified to handle it. Looking at the code, we have a payment interface and 3 classes that apply it. Each one represents a credit card, PayPal, and bank transfer payment methods. They implement their respective constructors, as well as the process payment method declared in the interface. Let's take a look at the following codes. This financial info class is not part of the factory method pattern. In this example, it's used to store various financial information of the user. In real-world Java code, it would be written with getters and setters. An object of this class is used as a parameter in the create payment method from the factory. Along with the factory's abstract class, we have factory classes of each payment class that inherit from it written. You can see how objects of financial info are utilized in different ways to create objects of the assigned classes. Lastly, it's the client code. This is how we create a financial info object filled with various information. In general, there would be much more data involved in real work situations. After creating factories for each class like this and running functions with the object of financial info as an argument, you can see results like this. Even if the way these classes are created changes, only the create payment method of the corresponding factory needs to be modified, so there are no parts that need to be changed in this client code. By delegating the creation of objects to the factory in this way, you can design a more flexible and expandable program. In the next video, we will look at the proxy pattern. The ninth pattern is the proxy pattern. A proxy is something or someone that substitutes for something else. As the name suggests, this pattern creates a stand-in for the target. You can think of it as a company's boss and their secretary. The secretary usually performs the job of representing the boss. Simple phone calls or minor approvals can be handled at the secretary's desk. However, when a task exceeds the secretary's ability or authority, they call the boss to take the front line. In this way, at the start of a program, a representative object is created and used, and under certain conditions, the real class object is created and used. This is precisely the proxy pattern.
Why would a mere object have a secretary I don't even have and goofing off?
There are primarily two cases in which this proxy pattern is used. First, when it's costly to create a real object. If you need to load large files or receive them over the network to create an object of some class, it's more efficient to load them only when absolutely necessary, rather than preloading them. Another case is when an object has sensitive features for security reasons. Normally, only the proxy object can be used, and access to the actual object is allowed only when it passes the security criteria. Let's look at the first example. This example is a program that handles large image files. We have an interface called ImageFirst. By applying this interface, we're going to make a real class and a proxy class. There is a method called display that displays the image on the screen first. To display the image, you have to actually load the image, so this will be the role of the real class. On the other hand, if it's a method that returns a file name, it doesn't need to load the image, so we can leave it to the proxy class. Now let's look at those two classes. There's the real image class, which actually handles the heavy work, and the proxy image class that takes on the representative role. Firstly, let's take a look at the actual class. It contains a method called loadFromDisk, which loads an image from the disk. It's a hefty task to load a large-scale image. The real image class runs this method in its constructor. In other words, it's a class that needs to load a large-scale image during instance creation. An instance of this class can directly implement and perform all the tasks defined in the interface. Now, let's look at the proxy part. The proxy class has an object of the actual class as a field. It's for calling when there's work the boss should handle. Even a proxy can handle the task of returning a file name. It can even have the additional feature of kindly telling you the extension separately. But when it's time to execute the display method, you need the boss now. The secretary first checks if the boss is in the office, and if not, calls the boss. In this process, an instance of real image is created and the image file is loaded from the disk. And at the secretary's request, the boss himself executes the display method. Lastly, we have the client code. You can see that only an instance of the proxy is created and used in the client. It's like the boss not taking the front line. The method of getting the file name is something the proxy can do on its own. You can see how meticulously the proxy performs its unique function of only fetching the extension. Now, if we run the display method, you can see that a message saying that it's loading the image is printed. We said the proxy could not perform display directly, right? It's the code being printed through the loadFromDisk method in the process of creating the real image class by the secretary calling the boss. After the real image loads the image file like this, you can see that the display is successfully executed by the real image. And afterwards, when the display is called, you can see that the method is executed directly without the image loading process. There's no need to summon the boss again if he's already in the office. In this way, this pattern can be used to delay the creation of a specific object until the point when a heavy task actually needs to be executed. By applying this, you can also use this pattern to cache the results of tasks that are also expensive. Here is the second example to examine other uses of this pattern. It's an interface of a bank account with deposit and withdrawal functions. There's no particular need to limit the deposit function, but the withdrawal function needs to be subject to high security standards to prevent anyone from using it. To do this, we create actual classes and proxy classes. In the real bank account class, it has both deposit and withdrawal functions like this. With this class, you can freely deposit and withdraw. If the proxy in the first example played the role of a secretary, this proxy performs a task similar to a security guard. It works like this by having an instance of real bank account as a field. The purpose is different from the first example, so it gets its value directly from the constructor. This proxy executes both the deposit and withdrawal functions through the actual class instance. That is, the security guard himself doesn't do anything directly. For deposit, it's like this. You call the method of real bank account without any restrictions. But in the case of withdrawal, it's designed to go through a security process. So, we verify whether the user has administrative privileges, and only when they have such privileges, we call the withdrawal function of the actual class. The appearance and the result used in the client code you can easily anticipate. Here too, you can see that only instances of proxy are created and used by the client. With administrative rights, you can freely deposit and withdraw like this. But with the rights of a general user, you can deposit, but the withdrawal function is limited like this. The advantage of the proxy method is that there is no need to modify the actual class, even if the security policy changes in the future. Because all security-related matters are entirely up to the security officer, the proxy, the actual class, is therefore free from this. By creating proxies that stand in for actual classes like this, we can optimize the performance of the program and design efficient access control logic. In the next video, we will learn about the observer pattern. The pattern we will learn this time is the observer pattern. This pattern is designed for a one-to-many relationship between a subject and one or more observers, where the observers are notified and respond whenever there is a change in the subject. It's like the relationship between an influencer and their followers. For an influencer, new followers or observers can appear at any time, and existing followers can also disappear. When the influencer posts content, the followers receive notifications and then react individually. Let's dive right into our first example. I've created the subject, which is the object of observation, and the observer as interfaces like this. When a specific event occurs in the subject, it notifies the observers through the notify observers method, and the observers receive it via the update method and perform the predetermined response. The subject has a method to add new observers and a method to remove a specific observer. Now let's take a look at the classes that employ each of these. The subject can be compared to a news agency that publishes new news, and the observer is a class of news channels that broadcast news received from it. The subject has a collection that can hold multiple observers like this. It holds a list of channels subscribing to the agency. When it signs a contract with a new channel, it adds its instance to the list, and if a channel cancels its subscription, it removes it from the notification targets. The core method of the observer pattern is this notify observers, which is executed when new news is released. It iterates over the observer instances in the collection one by one, calling their update method. It distributes news to all channels that are currently subscribing. The news channels that have received a notification process the received news to make a report. The news agency receives new news through the setNews method, and then it's set to run the notify observers method. Now let's take a look at the client code. First, we create an instance of the subject, the news agency, and create instances of the observers, the news channels, and add them to the agency's observer collection. Currently, these two channels are subscribing to the agency. In this state, when the agency publishes news, you can see both channels reporting the news like this. This time I will try to unsubscribe by removing the instance of channel 2 from the collection. The next published news is only reported on channel 1 like this. In such cases, when you need to implement a dynamic one-to-many relationship among various entities, the observer pattern can be beneficially used. This time, let's take a look at an example where there are various types of observers. It's an interface of a subject that publishes weather information and observers that display it in each of their own ways. You can see that the methods of these interfaces are similar to the first example. The weather data class, which applies to the subject, looks like this. Just like the news agency in the first example, it has a list of observers and methods to register and unregister them, and it also has an implemented method to send notifications to registered observers. This method is executed by this method, which inputs the measured weather data. It's basically the same as the first example. Next, we have classes implementing the observer interface. These are classes of 3 displays, each displaying information received from the subject in its own way. Like this, the update method is implemented to print statements in the format suitable for what they are assigned to. There's no need for me to explain the client code separately. You first create an instance of the subject and register instances of the 3 observers with the subject. Then, when the weather information is published from the subject, you can see it displayed in these 3 different ways. In this way, the observer pattern maintains loose coupling among objects. It automatically notifies numerous observers about a subject's state change, thereby enhancing the system's flexibility and scalability. In the next video, we will explore the Flyweight pattern. In this lesson, we'll look at the Flyweight pattern. This pattern is for when a certain object is needed multiple times or in multiple places. It's a pattern to save memory by sharing one instance, instead of creating a new one every time. Think about a book in your house. One person could read this book several times, or more than one family member might read it. If you had to buy a new book every time, it would be a waste financially and in terms of shelf space. If you need different books from what you have at home, you can buy one of each kind. If a book is already on the shelf, it would be wise to take that and read it. In case an instance of a class requires an instance with the same field value, it would be more efficient to reuse it in terms of computer resources. Let's take a look at the first example created based on the example we just heard. It's a simple class representing a book. It has a string field called title and a constructor that sets this value, and a read method that prints the string including this. The important point here is this title field. Since it's the only field of this class, if the value of this is the same, it means it's the same book. In other words, it means that there is no need to create more than one object with the same title value. To implement this, we create a class called a bookshelf. This class contains a hash map as a field. A hash map is a collection that stores values based on a unique key and its corresponding value. In this hash map, a string is stored as a key and an instance of book is stored as a value. The string contains the title of the book, making sure that no books with the same title are added. This getBook method, which is a static method, is an important part. It first checks whether the title received as a parameter is in the hash map as a key. If it's not there, it's a book that's not at home, so we buy a new one and put it on the bookshelf. If the book already exists, the instance of that book would be stored in this book. In this way, after purchasing a new book or taking a book already on the bookshelf, it is returned. With this statement, we can check if the book is newly purchased or you have taken it out from your existing collection. Let's now examine the client's code. You acquire the book Effective Java for the first time through the getBook method. With the printed statement, we can confirm that we have created a new instance of the book and put it in the hash map. Meanwhile, if you try to get the book with the same title again, you can see that since it's already in the bookshelf, it reuses the item stored in the hash map. In this way, if you append a book that doesn't exist before, you will be able to see the statement that we have created a new instance of the book. In Java, when you compare variables and constants containing class instances in this way, it can be shown whether they point to the same instance in memory. This way, you can see that 2 books with the same title are the same instance. This is about reusing the same object, rather than creating a new one with the same content, which can reduce memory usage. Next, let's take a look at an example of a class with more fields. There is a font interface to represent the font of a text, and a concrete font class implementing it. They are separated into interface and concrete class for extensibility. If you look at this class, you can see that it has 3 fields like this: font, size, and color.
So if any of these are different, it would be a different style?
That's right. It's only when all 3 are the same that it can be a reusable font. It may sound complicated, but implementing it is surprisingly simple. We create a hash map to store fonts that do not overlap when it comes to their keys. Depending on whether the font I am looking for is stored in the hash map or not, we either create a new one or reuse existing ones. The crucial part is what you choose as a key. You use a string that adds all the values of the 3 fields, namely font, size, color. Then, objects with the same font, size, color will have the same string for a key, preventing them from being stored repeatedly. Now, let's take a look at the client code. As you can see, the first and the second fonts have the exact same 3 values. So, when we take the first font, we generate a new instance like this. But the next one, we can see it reuses the one just created. You can see these 3 values are combined into one string down here and used as a key. Then, as the next font uses different values, we made a new instance like this. And the last font, as you can see, reuses the first one as they have the same values. The flyweight pattern is very useful in situations where the same object can be created multiple times, saving memory. Next time we will look into the abstract factory pattern. The 12th pattern is the abstract factory pattern. This pattern is similar to the factory method pattern we learned before, in that it separates the part that creates instances of classes. The difference is that while the factory method pattern deals with the creation of a single product, the abstract factory pattern is about the creation of a group of related products, that is, a product family. Therefore, it has a more abstract and complex structure than the factory method pattern. Let's jump right into our first example. We will create classes that represent the commonly used UI elements, buttons and checkboxes. First, we create each one as an interface like this. Here are the interfaces for the button and checkbox. This paint method serves to display these elements on the screen. In the example, we'll only deal with this method. The right side presents these 2 classes transformed for each operating system. As you see, we have classes for Windows button and checkbox, and for Mac button and checkbox as well. So, both buttons and checkboxes will be used as product lines that can be created in various versions depending on the environment. Now, let's take a look at factory classes. As you see in the abstract factory class, a factory is composed of abstract and concrete parts. First, let's look at the factory's interface. As you see, methods to create button instances and methods to create checkbox instances are declared. Remember, this button and checkbox are not concrete classes, but interfaces. On the right, you have the Windows factory and Mac factory, which implement the factory interface on the left. It's set up to create and return Windows and Mac versions of the buttons and checkboxes we saw in the previous code. This is how factories are concretized according to groups of products. Finally, we're going to look at the client part. In the previous examples, we considered the main class as the client, but in this pattern, we will define the client as the class that directly uses the main interface of the pattern. The main class will serve as an entry point to this client. Let's take a look at the client application class first. As you can see, it has instances of buttons and checkboxes as fields. Below is the constructor of the client. It takes an instance of the GUI factory as a parameter. It's the instance of this interface. So either an instance of a Windows factory or a Mac factory would be passed in. Now let's get back to the client code. You create instances of buttons and checkboxes according to the type of factory by using the methods of that factory. Finally, you use the paint method to draw all elements of the product line on the screen at once. Shall we now examine the code of the main class that uses this? First, you create an instance of the Windows factory. Then you put it as an argument in the constructor of the client, the application. Here, Windows buttons and checkboxes will be created. Now when you call the paint method, you can see a result like this being printed. The only difference in the section below is that the factory has been switched to Mac. Therefore, you can easily predict that such a result will occur. By choosing one of these factories to apply to your application, you can handle a specific version of products in the product line uniformly. Now, let's take a look at the second example. It's a program related to databases. The order in which I show the codes may be different, but the structure is the same. First, the three important parts of database-related operations are each written as interfaces. These connections, commands, and result sets will be implemented as class versions of MySQL or PostgreSQL, and on the right you have an abstract factory that creates instances of these three as an instance. This factory is also expected to be implemented in a MySQL or PostgreSQL version. The following codes are the implementation of the products in a certain version of the product line. Connections, commands, and result sets can be seen as created in such MySQL version, and also in PostgreSQL version of classes. You can easily predict that the following code is their factory, a factory that creates instances of the MySQL product family, and a factory that creates instances of the PostgreSQL product family. Depending on which of these is instantiated on the client, the products that get created will vary. Finally, here's the client and the main code. The structure of the code is the same as the first example. This database client plays the same role as the application in the first example. It uses the factory passed in as a parameter to create instances of connection, command, and result set. Then it executes the methods of each one in a batch. So when you use MySQL's factory like this, you get output like this below, and when you switch to PostgreSQL's factory, you'll see different results accordingly. In this way, by using an abstract factory class, you can consistently create a product family of related objects and increase flexibility and scalability by not depending on concrete classes. Next time, we will learn about the Mediator pattern. We'll be looking at the Mediator pattern for our 13th pattern. As the name suggests, this pattern involves placing a mediator between several objects. There are programs where multiple objects of the same type interact and operate. If they're directly connected, such a complex dependency relationship would be formed. One object would have to remember many other objects, and any changes to a particular object would affect the rest. The Mediator pattern introduces a mediator between them, creating a central point of communication. By having the objects depend on the mediator, it helps lower their coupling and improves maintainability. Let's start with the first example. It's a chat program. The mediator here will play a role in delivering messages among user objects. It's written in the form of an interface like this. There's a method declared to send a given string as a message from a specific user to other users and to add a given user to the management list. These are implemented in the class on the right, which applies the said interface. This class has a list of users like this. The method to add a user puts the user received as a parameter into this list, and the method to send a message sends it to all users in the list, excluding the sender. Next is code about the user. On the left is an abstract class, and on the right is a concrete class that inherits from it. You can see that each user has an instance of the mediator as a field like this, not other users. This is because all communications are made through this mediator. When a user sends a message to other users, they call the send method of this mediator with the message as an argument like this. So, as we saw earlier, the mediator calls the receive method of users, excluding the relevant user from the list. This is the very method that receives messages from other users. In this way, communication is formed among users through the mediator. The client code and its execution results are as follows. You create an instance of the mediator first, and then create instances for the 4 users like this. After enrolling all users in the mediator's list like this, users can enter the chat room. When one user sends a message like this, the other users receive the message via the mediator in this way.
It seems like it would have been really complex if you had written the code with just the user and the client without a mediator.
Yes, indeed. By separately creating a mediator to carry messages among users, we can simplify the interactions between objects and even improve the scalability of the code. The second example is another kind of mediator pattern. You might not recognize it as the same pattern as the first example solely by looking at the code, because the structure is different. Imagine a program acting as a control tower at an airport between flights and runways. It's about deciding whether to allow a flight to land or not, depending on whether the runway is occupied or empty. The differences from the first example are that the mediator interacts between objects of different kinds, and the role of the mediator is more passive. Let's look at the example code. First, it's the mediator part. Here are the interface of the mediator and the control tower class implementing it. As you see, this mediator does not have instances of the subjects to mediate, like a list. As seen here, only two methods are implemented. A method that returns whether the current runway is available, and a setter method that sets it to true or false. This is the only role of the mediator here. Now, let's take a look at the class of the flight and the runway. The flight has a landing method. First, you check whether the runway is available through the mediator. If it is, then the flight lands on the runway like this. During the landing, the runway becomes in use. So through the mediator, you change the value to prevent other flights from landing. If the runway is not available, then a message indicating that it is on standby for landing is displayed like this. The runway changes its availability to true through the method called clear after a flight has landed. Then another flight would be able to use the runway. Lastly, here's the client code. First, create an instance of mediator, the control tower, and pass this as an argument to the constructors to create instances of flights and runways. Note that there is no process of registering flights or runways with the control tower here, just this one-way relationship. The initial state of the runway is available, so the first flight lands without any problem like this. Then, it changes the state of the runway to in use. Therefore, the second flight can't land immediately after that. For the runway to become available, the runway must use the clear method to switch status. Then, the second flight can land like this. Just like this, there are usage formats where the mediator only performs the role about as much as a signpost in use. So, we just learned how to control interactions among objects using the mediator pattern. Next time, we are going to look at the visitor pattern. In this session, we will explore the visitor pattern. This pattern allows you to add new features without having to modify existing classes. Let's suppose there are classes that have functions of different shapes. They would probably be concrete classes derived from a specific interface or abstract class. They might each have methods for calculating their respective areas. But then, if we later need a functionality to calculate their circumference, we'll have to change the classes to add the methods. If these are classes that frequently add functionalities, then you'd have to go through a cumbersome process every time. In the visitor pattern, it's not these themselves that have functions, but they're made to accept visitors with functions. For example, create such a visitor to calculate the area, and let this visitor visit each shape to measure the area. So, this allows you to add as many visitors as you want, such as ones that calculate the perimeter afterwards. Let's take a look at the first example dealing with this. It's about the interface of shapes and classes of circle and rectangle applying it. The circle has a field, constructor, getter and setter related to its radius like this. And the rectangle also has the same components for width and height. The important thing in this example is this method. It's a method that accepts visitors. It allows the visitor given as a parameter to call the visit method with the instance of the class itself as an argument. In other words, it's a method that welcomes the visitor's visit. Next up, we have the visitor interfaces and the classes implementing them. These classes each have a feature to calculate the area and the perimeter. In statically typed languages like Java, they need to implement two versions of the visit method like this. It's called method overloading, where you implement a separate method for each data type of the parameters. This is because these visitors can visit both circles and rectangles. So, in this way, methods to calculate the area and circumference of a circle have been written, and also the methods to calculate the area and perimeter of a rectangle have been formulated. If there are additional shapes, such as triangles, to deal with, the methods for these visitors will also be added accordingly. Now, let's take a look at the client's code. First, we create instances of a circle with a radius of 5 and a rectangle with a width and height of 4 and 6 respectively. We also create instances of a visitor that calculates the area and a visitor that calculates the perimeter. If the area calculating visitor visits both the circle and the rectangle, you can see that the areas are calculated and displayed as shown on the right. Likewise, you can see that the perimeter calculating visitor calculates the perimeters of the two shapes in the same way. If there are other functions that need to be performed with these shapes, you just need to create a new visitor. The second example is a program related to the file system. We will create a visitor that can be applied commonly to files and directories. Let's look at the code. It's a class of files and directories that has implemented the interface called file system. Since we've applied the visitor pattern, we have implemented methods to accept the visitors like this. Both files and directories have names, so there are fields and getters for these names. A file has its own size, so it also has a field and getter for its size. On the other hand, a directory has a list of file system elements it contains, namely files and directories. So, this folder contains a list of other files or folders inside it. This is a method that adds a given file or directory to that list. In other words, puts another thing in that directory, and this method is a getter that returns that list. Now, let's look into the visitor interface and the classes that implement it. A visitor that measures the volume of the visited elements, in other words, the total size. And a visitor that finds a specific file with a given file name. These functionalities also work differently in files and folders, hence are separately implemented via method overloading. Measuring the size of a file is simple. You just get the value of the size field of the file and add it to the total size. But in the case of directories, you have to add up the sizes of all the files within them. Therefore, you need to visit each file and directory within that directory using a loop. If the visited element is a file, you add its size to the total size. If it's a directory, you'll undergo a recursive action where you visit each element within it one by one. Those of you who are not familiar with the concept of recursion may need to carefully examine the code to understand this part. Then, simply calculate the capacity of the specific file or directory and return the total capacity through this getter. Finding files by file name also works on the same principle. If applied to a specific file, the file is saved as the found file when the file name matches the parameter. When applied to a directory, it visits each element inside, looking for a file with the given name. If there is a file with the given name inside, that file will be saved as the found file. The file you found is then returned using this getter method. This example has somewhat lengthy client code. First, instances of files 1, 2 and 3 are created like this. Then we create a directory called folder 1 and put file 1 and 2 in it. Likewise, create folder 2 and put file 3 in it. Finally, when you create a root folder and place folder 1 and folder 2 in it, you end up with a file system structure like this. Now, it's time to use the visitors we've created. First, create an instance of the visitor that calculates the size, and let this visitor visit the root directory and perform its operation. The visitor will recursively traverse through the folders in the directory, summing up all the file sizes. Now, if we print the result, like so, you can see the result, 600, that was stored in the visitor instance has been returned. Next up is a visitor looking for a file called file3.txt. Similarly, by ordering it to visit the root folder like this, it recursively searches for the file in question, and it ends up printing the information of the instance with the given file name. Like this, we have explored the visitor pattern. This pattern can be particularly useful in situations where the object structure is stable, but the operations that must be performed on the structure often change or are added. Next time, we will look into the builder pattern. The 15th pattern is the builder pattern. This pattern divides the process of creating an object into steps, handling it flexibly. Think about the process of making a pizza. Let's assume that there are 3 stages. A stage of kneading and shaping the dough, a stage of spreading sauce on top of it, and finally, a stage of adding the toppings. Let's think that all these processes must be done at once. If the sauce is not ready or the topping has not been chosen, you can't even start kneading the dough. You can start working only when all the ingredients are ready and the menu is confirmed. On the other hand, like a save point in a game, what if you can proceed only up to the desired stage and then wait? You can knead the dough first and wait for the sauce to be ready, or you can spread the sauce first and add different toppings according to the incoming order. Let's look at this example as our first sample code. Firstly, we have a class for pizza like this. This is the first time we have an inner class in the patterns we've covered in this series. Inside the pizza class, there's an inner class named Pizza Builder class. It doesn't have to be an inner class, but as it has a close relationship with the pizza class, we often make it as such. If you look at the constructor of the pizza class, you can see that it is declared as private. In other words, it's set up so that the constructor of this pizza class cannot be called from outside. The only one that can call this is the inner class, the Pizza Builder. And what goes in as parameters to this constructor is an instance of the Pizza Builder. Using the dough, sauce and topping fields that the Pizza Builder's instance possesses, an instance of a pizza is created. Up next, we have methods in the Pizza Builder instance which assign values for the dough, sauce and toppings. In fact, in this example, it doesn't matter if the order of these three processes is changed, but there are programs that need to follow the order due to the nature of the product. Once values have been assigned to those three fields through these methods, finally, you can use the build method to return the completed pizza. Before we move on to the client code, there's something we need to pay attention to in these three methods. They return the instance of the Pizza Builder itself, which is the object. You need to understand this part before we proceed. Now let's look at the client's code. Like this, we will try making a pizza in two ways. The first is to execute all the processes at once, one after the other.
You know, calling methods consecutively like this, is it what they call method chaining?
Correct. Remember I said that these methods of Pizza Builder all return the Pizza Builder itself? First, an instance of the Pizza Builder, with no value entered yet, is created through this Pizza Builder constructor. Since it is an instance of the Pizza Builder, it should be able to execute all of its dough, sauce, topping and build methods, right? The dough method puts the given string in the dough field and then returns itself, which is an instance of Pizza Builder. So the value returned at this point is an instance of the Pizza Builder that has a thin crust as its dough. Therefore, it can also execute the sauce, which is yet another method of the Pizza Builder. At this point, the sauce field is filled and the Pizza Builder itself is returned again. If executed until here, a Pizza Builder with all the fields filled, including the topping, is returned, right? Finally, when the build method is executed, the pizza constructor is called and the completed pizza is returned. That's why you see a string like this being printed. For those of you who don't understand why the result of printing an instance of a specific class appears as this string, it is because it is the result of executing the toString method of that class. This time, we will make pizza in a way that makes more sense to use the builder pattern. Let's assume that the sauce is not yet prepared and the topping menu has not been decided. Like this, we first knead the regular dough. This Pizza Builder instance will be in a state where only the dough field has a value. Then, when the sauce is prepared, run the corresponding sauce method like this to put a value in the source field of that instance. Finally, by running the topping method and putting a value according to whether it is vegetarian, it prepares to return the pizza. Now, use the build method to create an instance of the pizza. And then, if you print it out like this, you can see the result like on the right.
It feels like it's a pattern used when creating instances of a class that's quite complex.
That's right. We will take a look at a sample code that you can often see in the field as the second example. It's a class that represents an HTTP request and a builder written as an inner class. The class for the HTTP request has these fields. Not all fields are always filled. If you look at the constructor of the builder, you can see that only the values corresponding to the method and URL are received as parameters. You can tell that these two fields are essential data. These three methods are used to populate the remaining fields. Because these also return instances of the builder, you can use method chaining. For headers and parameters, Since they are hash maps, methods for adding keys and values are written like this. This builder also uses the build method to ultimately return an instance of the product. Lastly, let's look at the client code. We're going to make two instances with different fields being filled. Both start with the values of the method and URL, which are essential fields. And the header information was also added in this way as a pair of a key and a value. The first object uses the get method and thus inserts the parameters keys and values, while the second object, which uses the post method, inserts the body's value as a string. After filling in the necessary fields like that, build to create an instance of the HTTP request. Now if you print them, you can see each result as on the right. In this way, by using the builder pattern to control and encapsulate the complicated process of object creation step by step, you can flexibly create objects with various configurations. Particularly when creating an object with many optional parameters, it greatly enhances code readability and maintainability. Next time, we will look at the Decorator Pattern. Today, we will learn about the Decorator Pattern, which is the 16th pattern. This pattern allows you to add desired features to a specific object dynamically and therefore allows combinations. The concept of dynamic addition may not be clear, so let's jump straight into an example. Think of a coffee menu at a cafe. How would you allow orders of basic coffee with added sugar or milk? First, one way could be to create each combination as its own menu item, like basic coffee, coffee with only sugar, coffee with only milk, coffee with both, and each would take up space on the menu. In programming terms, this means writing each combination as a separate class. This method will not only have a lot of overlap, but also the number of combinations will double each time a variable, such as decaffeinated or vegan, is added. A better solution would be to separate options like sugar and milk into a separate addition menu. Then, with this simple menu, customers can easily create the combination they want. Let's take a look at the code. There are a coffee interface and simple coffee class implementing it. There are two simple methods declared and implemented in these. Firstly, there's a code to print the description, which, in case of simple coffee, simply prints out its name. And as for the getter that obtains the price value, simple coffee returns 5. Now, we'll use decorators here to add sugar and milk. This decorator also implements the coffee interface. So, the instance of the decorator gets a data type of coffee. What is notable is, the decorator has a coffee field type called decorated coffee inside it. In other words, there is another coffee inside the coffee instance. By using the decorator's constructor, we get another coffee to put in this field. This part might be hard to understand, but please follow along until we look at the client code. Before moving on to the next code, another thing you should look at and remember is the methods overridden by the decorator call the corresponding methods of this decorated coffee. Pause this video for a while and take a look at these codes. Next are the milk decorator and sugar decorator classes that inherit from the coffee decorator. As I just mentioned, because they inherit from the coffee decorator applying the coffee interface, their instances also become instances of coffee. They are also overriding and implementing the methods of coffee like this. First, let's look at their constructors. Like this, it takes another instance of coffee as a parameter and uses super to directly call the constructor of the parent class. Remember that the constructor of the parent class, coffee decorator, stored it in the decorated coffee field? Because these classes are subclasses of coffee decorator, they inherit and possess that field. So the coffee instance received as a parameter in the constructor is stored as the value of the decorated coffee field. Now let's take a look at the methods of coffee that they have overridden and implemented. Even if this part isn't understood at the moment, please follow along for now. Each method first calls the corresponding method implemented by the parent class using super. This is like what we saw here, calling the method of decorated coffee stored in the field. In other words, it is calling the method from this coffee instance that was taken as a parameter in the constructor. And as you can see, it attaches or adds unique values of the class to the result. Please take a look at this part for a moment before moving on to the client code. Finally, here's the client's code. Let's first make a simple coffee without using any decorators. When we append the description and price like this, we get the result as shown on the right. Now let's take a look at a coffee with milk added using a milk decorator. First, create an instance of the simple coffee, then pass it as an argument to the constructor of the milk decorator, thereby creating an instance of the milk decorator. So, this instance of the simple coffee is stored in the decorated coffee field within the instance of the milk decorator. Now, when you execute the getDescription method from this milk decorator instance, it first takes the description value of the simple coffee stored in its field. It then returns the appended value from the milk decorator that wraps it. You can see that the method that gets the price returns the sum of 5, which the simple coffee returns, and 1.5, which the milk decorator adds. This is how you make coffee with both milk and sugar. You create an instance of the milk decorator by using the instance of the simple coffee as an argument, and then use that to create an instance of the sugar decorator. If you print the result of executing the instances method, you can see the value added by the milk decorator to the result of executing the simple coffee's method, and in addition to this, the value added by the sugar decorator is combined and returned. In this way, you can dynamically create instances with the desired features by layering instances of basic classes with decorators for necessary features. Our next example involves a program that deals with text styling. Those of you who have learned HTML will know that when you surround text with the B tag like this, the text becomes bold. Moreover, you can surround it again with the I tag to have bold and italic text, and the U tag will add an underline to this. Each tag can be used individually, or as shown, in complex layers. Let's look at this through our second example code. Its structure is the same as the first example. There is a text interface and a plain text class that applies it, and of course, a text decorator also implementing the text interface. This decorator also holds an instance of the text as an internal field. This will be the target of decoration. Next, let's look at specific decorator classes. I don't need to expressly mention that they are descendants of the text decorator. Thus, decorators add style by wrapping the results of the method execution of the targeted object with B, I, or U tags. Finally, let's look at the client code. First, we have plain text without any style. Now, if we create a new instance by putting this instance into the argument of the bold decorator, it will return text wrapped in B tags with the same method. If you wrap this again with the italic decorator, it gains a slanted style. Finally, by using the underline decorator, you can generate text that has lines drawn underneath it, or you can apply slanting and underline at once, like this. In this way, by using the decorator pattern, you can dynamically add new responsibilities and behavior to an object without modifying the existing code. This allows you to increase flexibility and expandability, avoid class explosion problems, and adhere to the single responsibility principle. Next time, we'll explore the command pattern. The pattern we will learn this time is the command pattern. This pattern turns commands into objects and stores them in a collection, allowing for execution or cancellation of the commands at any time, as well as diverse applications such as logging. Let's take a look at our first example right away. This is the class of the light, the receiver, which is going to take the commands. It has methods to turn itself on and off like this. We are going to create classes for the commands to be given to this light. These are the set codes. There's an interface called command, and a method named execute is declared. Two classes that apply this have a field to contain an instance of the light, and a setter to assign a value to it. Their execute methods are respectively implemented to turn this light on or off. So, instances of these two classes are objects that encapsulate the command to turn on and off the light. Now, let's take a look at the invoker class, which mounts and executes these commands. This class has a field that stores an instance of the command and a setter for it. That is, this field can be equipped with the command to turn on or off the light, and when you call the method to press the button, the corresponding command gets executed. The one on the right is client code. First, we create an instance of the light like this, and then instances of turning on and off commands, and an instance of the invoker, the remote control, to be equipped with these. Now, set the command to turn on the light to the remote control. When we press the execute button, this message that the light is turned on, like in the comment, comes out. When we change to the command that turns off the light and press the button again, we can see the message that the light is turned off like this.
I understand the principle, but why do we specifically have to use this pattern?
I will clarify this by introducing a program where you can distinctly see the benefits of the command pattern as our second example. You know how text editors and various other editing programs have undo and redo functions, right? These functions are typically implemented through the command pattern. All of the user's actions are stored in the invoker's undo and redo stacks as objects. If operations such as inputting or deleting occur, these will be stacked in the undo stack, so they can be reversed in backward order. When we undo the tasks stacked, they are then moved to the redo stack, so they can be re-executed if needed. Here is the code of the text editor, our receiver for this example. As you see, a content, which is a field with string builder data type, gets its value from the constructor. Java String Builder allows you to add or remove given strings to your string, or it also provides functionalities like returning a part of the string. Once you've finished the necessary operations, you can return the final string using toString method. The commands in this example will deal with these three methods. Next, we have the command interface. As you can see here, execute and undo methods are declared. And we have the text insertion command class and the text deletion command class, where this is implemented. These are instances of the text editor, strings to be added or removed, and the integer values of the positions where they will be added or removed. And we get these from the constructor. Their execute methods each perform the task of adding and removing the given text. The undo method, for the corresponding string and position, calls the execute code of each relative class. The undo of a text insert command executes a delete command, and the undo of a text delete command executes a text insert command. Understanding this invoker's code is essential. An invoker has fields for stacks for undoing and redoing, like this. A stack is a data structure where the last in is the first out. Let's first look at the method that executes the command. This way, it first calls the execute method of the command, and it adds it to the undo stack so it can be undone. Because redoing can only be done immediately after undoing, the redo stack is emptied like this. Now, let's run the undo method. First, you take out the command at the top of the undo stack. Once removed, call its undo to perform the opposite action. And so you can revert it with a redo, you add it to the redo stack. Lastly, we have the redo method. It pulls out one from the redo stack and then executes it. And then this is placed back in the undo stack. This way, the execution, undo, and redo of commands take place. Lastly, we'll look at the client code. First, create an instance of the text editor and the invoker. Then, create an instance of a command that inserts the text hello at the 0th position like this and execute it. Next, make a command that inputs the text world at the 7th position and also execute it. Now, if you extract and output the result string, you can see that it produces a result like the one on the right. And when you call undo, it removes the last inserted word, so you're left with just hello. If you call redo, it operates in reverse, and you can see that the word is attached again. Now let's execute a command to delete characters from the 0th to the 7th position, which will erase the previous hello. Then, when you undo, the opposite happens. The characters are reinserted, and everything returns as before. We have just learned about how to effectively use the command pattern in real-world scenarios. In the next session, we will explore the Memento Pattern. The 18th pattern is the Memento Pattern. This pattern allows you to save the internal state of an object, like a snapshot, and restore it when needed.
Like saving the game while playing?
That's correct. We'll take a look at a program that saves game progress as the first example. This Game Memento class is a class representing a save state of the game. An instance of this game memento is created and kept each time the game is saved. It receives and stores the level and score at the time of save from its constructor and has these fields, and it has getters for them. It's a simple class that simply stores values. Next is the game class. It is the subject that saves the memento and restores data from it, known as the originator in this pattern. A game also has fields for level and score, and there are setters that assign values to them. And when you run the save method, it creates an instance of memento with the values of those fields as arguments and returns it. It's like exporting the current progress of the game as a snapshot called a memento. Conversely, the restore method restores the level and score values to the values stored in the given memento. Next is the caretaker that stores and manages mementos. In this example, we use an array list like this. There are methods to add a new memento given as a parameter, and to get a memento of the index given as a parameter. In fact, the caretaker in this example can be replaced simply with an array list, because it only has these features. Next is the client code. First, create instances of the game and caretaker respectively. Then, progress the game so that the level is 1 and the score is 100. Export this to a memento and store it in the caretaker. It will likely to be stored at index 0 since it's the first save. Continue to level 2 with a score of 300, then save it to be stored at index 1. Finally, proceed like this to the state of level 3 with a score of 300 in the game. Now, let's restore the saved states. If you load the memento from index 1 from the caretaker into the game, you can see that it goes back to the state at level 2 with a score of 200. Similarly, if you load the memento from index 0, it will be back to the first save state. In our previous video, we looked at an example of implementing an undo function in an editor program using the command pattern. Now, we will try to implement this with the Memento pattern. While the command pattern stores all the document editing actions as units called commands in a stack, in Memento pattern, the edited state of the document gets stored as a memento. In cases where the document has a small size and is not modified frequently, the more simply implemented Memento pattern can be more efficient. Let's take a look at the code. It's about the memento and originator of the document. The memento of the document only stores a single string called content. It only has a constructor that assigns a value to this field and a getter that returns it. The document uses the string builder, which is also dealt with in the command pattern, to edit the text and export it as a string. There are methods for creating and exporting the current document contents as a memento, and for receiving a memento and restoring the document. Next, we have the caretaker class, which is a history, and the client role of the editor class. In this example, we use a stack to store the mementos of the documents. In fact, given that there are only push and pop methods in this example, you could substitute it with a stack. If you want to add a redo function, like in the command pattern, then a caretaker would be necessary. The editor on the right has documents and history as its fields from the moment it is created. When you execute the write method of the editor, it first saves the previous state to the history, then uses the write method of the document to add the string to the text of the document. If you execute the undo method below, it pops out the last memento from the history and use it to restore the document. Lastly, we have the main method. In this example, since the editor we just reviewed acts as a client, the document, memento and caretaker do not appear in the main class. First, insert text into the document twice like this, and if you extract and print it, results will appear as shown below. Now, let's call undo to revert the document to the state before the last edit was executed. You can see that only the string that was initially input is printed like this. Now insert a new string, and when you print the result, you can see the currently edited content again. Like this, the Memento pattern helps to save and restore the internal state of an object without directly accessing it from outside. Next time, we will look into the prototype pattern. The 19th pattern is the prototype pattern. Instead of creating new instances of a class with a high creation cost each time, this pattern allows you to use by replicating a once created prototype. When you need to create multiple documents with the same content, it could take a lot of time and effort to create each one individually. But if you finish one and then copy it, you can get things done much faster. The prototype pattern implements this by adding a self-replication function to the object being handled. Let's look at the first example. Since this is an ODP course, I wrote the prototype interface directly like this. But actually, Java provides an interface called Clonable as a basic library, so it is usually used. Most other languages also provide methods for prototype cloning, so please check this according to the language you are using. This prototype interface possesses a method named clone, which returns an instance of the same prototype. The person class on the right applies the prototype pattern, meaning it's a class that can be written to allow the instance itself to be duplicated. This class has two constructors. One receives the values of each field as individual parameters, assigns them, and returns the result. The other one takes an instance of the same class as a parameter and assigns the values from that instance's fields. And the clone method of this class generates an instance by treating itself as an argument for the second constructor. So, it's a method that duplicates itself, like feeding myself into a copier to produce a copy of me. This isn't the only way to do it. You can implement any way that allows the class to produce a new instance using its own field values. The remaining two methods are a simple setter for the address and a method for the instance to print its own information. Now, let's take a look at the client code. First, we create an instance of the person like this. The last field, the address, is 123 Main Street. When we call the display function, this is what's printed. Now, clone the instance and assign it to a variable called cloned. At this point, the values of the fields will be the same as the original. Then, use the address setter to change the address to 456 Clone Street. Now, when we print the information of these two with the display info method, you can see that while the name and age are the same, the addresses are different. The fact that the original address doesn't change means that not just a reference copy, but all fields were copied. When you need to create instances that involve heavy operations, like using the network or querying a database, using cloning like this, you can save a lot of time and resources. This time, we're going to look at a program that creates various document templates as prototypes and uses them by duplicating them. Here's the second example. As you can see, there's a prototype interface, a document interface that inherits from it, and a text document class that applies it. The text document class also duplicates itself and returns it using the clone method. The getter method of the document interface is also implemented using a field called content. Next is the manager class, where templates will be managed. As you can see, it manages various templates using a hash map. It basically stores a specific format of a document draft along with the template name in the hash map as parameters.
It's similar to what we saw in the Flyweight pattern, isn't it?
Yes, you're right. The difference, however, is that while the Flyweight pattern shares the same instance stored in the hash map, this pattern duplicates the instance taken out from the hash map and returns that duplicate. The original stored in the hash map remains unchanged, even when the duplicate is modified. Now, let's take a look at the client code. We'll start by creating two templates. Create a template named welcome like this, with the same content as the string below. Also, create the meeting template with the basic content and add it to the templates. Now we make a new document using the welcome template we created at first. Then we change the part of the content we want like this from the basic content. Now if you print the content, you can see that the results come out in the format set in the template like this. You can see that you can also create a copy of the meeting template like this and modify the contents for use. In this way, the prototype pattern effectively handles the creation of complex objects, and by cloning and reusing objects, it is useful for optimizing performance. Next time, we will explore the chain of responsibility pattern. The pattern we're focusing on this time is the chain of responsibility pattern. This pattern passes a request along a chain of eligible objects for processing. In this pattern, several objects like this pipe are used. Each object has two essential features. The first is the ability to process the given request. Each object performs its own function for the given input. The second is the ability to link another same type object as a successor. The request processed by the preceding objects is passed on to the next linked object. Classes of such objects are written as many as the number of tasks. And you can create a chain of tasks by connecting instances of these in various combinations as needed. For example, a chain connected like the one in the middle will perform the green, blue, and orange tasks sequentially for a given request. Let's look at the first example. It's code of handlers that process numbers given as parameters. There's an abstract class called handler, and there are 3 classes that extend from it. Each handler has a field called next, which is of the same handler data type. This points to another handler instance that will be linked behind the particular instance. setNext is a setter that puts an instance of the given handler as a value in this field. In other words, this method is used to designate the next handler for each handler. The abstract method called process allows each handler to perform its own operations for the given task. The handle method, which will be called from the outside, first calls the process method to execute its own tasks. Then, if there is a connected next handler, it calls the handle method of that handler. Over on the right are the handlers that implement the process method inherited from this. Their process methods print out a designated phrase when the arguments they receive as parameters are positive, even, or multiples of 3 respectively. Now let's move on to the client code. First, create instances of these 3 handlers like this. They are not connected yet. Now connect the even handler behind the positive handler like this. And if you connect the divisible by 3 handler behind the even number handler, these 3 handlers will be connected in a chain like this. Because the positive handler is at the front, if you put a number in this handler, the rest of the handlers will also be processed. If you put in -2, it goes through 3 handlers and it is printed as like this. In the even handler that it's even. If you put in 4, the value is output from both the positive handler and the even handler. In the case of 6, since the value is output from all 3 handlers, you can see such a result.
So, like the Decorator Pattern, we can make a combination of features at runtime, like connecting toy trains?
That's right. You can assemble the handlers you want in any order you want. In the second example, the execution condition is determined from the outside. First, an enumeration called log level is used. There are 3 levels: information, debug, and warning. In Java's enumeration, the ordinal of the one coming later returns a larger value. There is a setter in the abstract class called logger on the right that connects the next logger. Let's take a look at the method called logMessage of this class. This method runs the write method below when the log level value of this instance is equal to or smaller than the given level value. And, like in the first example, if the next logger is connected, it runs the same method of the connected logger. Here are 3 concrete classes inherited from the logger. There are console, file, and network formatters of loggers. They all take the log level values from outside through the constructor. That means, depending on what value you put in this constructor, each instance's log level is determined, and each logger format prints out differently like this. Lastly, it's the client code. It creates logs in network, file, console formats while setting each level to warning, debug, and information in order. These are sequentially linked in the order of network, file, console, and saved in a variable called logger chain. Now, if you try to output the logs at the lowest level, which is the information level, you'll see that the message is only displayed in the console logger, as shown on the right side. That's a logger class designated for this level. Now the logs of one level higher, the debug level, are output in both the file logger and console logger. You'll see that the logs of the highest level, the warning level, are output on all 3. This pattern separates the sender and receiver of a request, thus allowing multiple objects to have the opportunity to handle the request. It lowers the coupling among objects and increases the flexibility and scalability of request handling. Next time we will learn about the composite pattern. The 21st pattern is the composite pattern. This pattern allows you to represent part-whole hierarchies by configuring objects in a tree structure.
Isn't this the file system we saw in the second example of the visitor pattern earlier?
Yes, you could say a simple form of the composite pattern was also used in that example. All elements that make up this tree structure are called components. Among them, those elements that can have other elements as subordinates, like these directories or folders, are composites. And elements that can't have subordinate elements, like these files, are called leaves. In the composite pattern, the client can handle individual objects and composite objects without distinction. The first example will implement a file system in more detail than the previous example. First, this is the file system component interface that includes both individual files and composite directories. As you can see, it has getters that return the size and name, and a method that prints the name. On the right is the class of the file applying this. A file has both a name and a size, and it receives them through a constructor. Methods that return them like this are implemented to return the values of the corresponding fields. Unlike directories, the file actually occupies space, so you can see that the size is returned through the getter like this. PrintName is simply a method that prints the file name. Next is a class of the composite, directory. This class also applies the file system component, so it belongs to the same category as files. Since directory is a composite that can hold other components, it has a list of file system components like this. Files, which are leaves, and other directories, which are composites, can be included as sub-elements here. Firstly, there is a method that takes another component as a parameter and adds it to the list. And conversely, there are two methods that are overloaded to remove a specific element from the list. One is a method that takes the reference of the component to be deleted itself as a parameter. The other is a method that takes the name of the file or folder as a string parameter. Since the directory itself doesn't take up space, the getter that gets the size of the directory calculates the total size of the files in the list. As we go through each element in a list, if the element is a file, we get its size and add it. If the element is a directory, we recursively get the sizes of all the files inside and return the sum. The printName method also prints its own name and the names of internal elements recursively. Now let's look at the client code. First, make instances of two files like this. Then create a directory called subfolder and create and add a file named subfile inside. Finally, make an instance of the directory that will be the root folder and add the files and directories you've just made inside. If you run the code on the left in this state, the result on the right will be printed. The printName method of the root folder is executed recursively, printing all the names of files and directories inside. Likewise, the method for calculating size also returns by summing all the sizes of the files among the internal elements. The next is the result when a file is deleted and then printed. I deleted the image file based on its name. Finally, this is the result of deleting the subfolder. This time, you can see the delete method being run with the instance of the directory as the argument. With this pattern, you can easily implement a tree structure composed of leaves and composites. Next, let's look at an example where there can be several types of leaves and composites. The composite pattern can also be used to implement such a UI. In the UI, there are elements that can include sub-elements and those that cannot. These buttons, for instance, do not carry other elements inside them, so they correspond to leaves. This text box can also be considered a leaf. The panel that encompasses them would be a composite, and the window that encloses all of them also corresponds to a composite. Let's delve into the code now. First, we have the interface of UI components. The render method will be used similarly to the printName method in the first example. And in this example, methods for adding and removing components are also declared in the interface. Now here are the classes of buttons and text boxes, which represent the leaves. The methods for adding and removing other components in these classes are set up to throw exceptions. Strictly speaking, this code violates the interface segregation principle, one of the solid principles. However, in practice, this kind of implementation is sometimes done for the sake of maintaining consistency among classes or in small-sized systems. The button class takes a label, and the text box class takes a text from the constructor, and the render method is there to print out information about the corresponding element. This time, we'll be talking about the classes of panels and windows, which are composite objects. They possess lists that contain subcomponents, and methods for adding and removing elements are implemented in this way. For the render method, it outputs its own information and then calls the render method of the components it contains. This Java code is a code that calls the render method from the elements contained in the list. I don't need to explain the client code and its execution result to you. First, create leaf components like this. Then, create a panel and add those elements to it. Finally, create a window. Add that panel to it. Now you can see the same result as on the right when this is rendered. If you remove the cancel button from the panel and render it again, you can also see the result where the button has disappeared. Like this, by using a composite pattern, you can manage structures where certain objects include other objects in a simple and flexible way. Next time, we will learn about the Iterator pattern. The 22nd pattern is the Iterator pattern. The Iterator pattern is a complex one that is more difficult to understand and implement than the patterns we have learned so far. However, fortunately, It is very rare that you will need to use this pattern in practice. This pattern is used to interpret and execute the syntax of a specific language or query. It parses text and differentiates it into keywords, operators, variables, etc., and performs operations according to them.
So, would it be used in something like an IDE or a database system?
Yes, it is also used in various places, including all kinds of script engines, parsers, expression processing programs, etc. However, the task of developing such programs is not common, so it will be sufficient to know roughly what this pattern is. In this video, we will have a glimpse at how the interpreter pattern processes such codes and queries. Let's first take a look at a part of a program that runs this integer operation. There's an interface like this called expression. Expressions refer to all elements that can return a certain value, that is, can be replaced with a certain value. For example, this part literally returns the integer 5, and this part is the result of adding 2 to 5, so it returns 7, and this part returns 4. In this way, an expression can become a standalone element or a combination of multiple expressions. And this interpret method is a method that returns the value represented by the expression. In other words, expression classes that apply this interface must necessarily output the result value through this method. First, we will look at the class of numerical expressions that return integer values as they are. This is a numeric class that applies the interface of the expression like this. It is a simple class that represents one number, so there is an integer field and a constructor that puts a value in it. The interpret method is implemented to return the number value contained in the corresponding field. Next, we have classes of expressions that add and subtract the given two sides. You can see these also apply the expression interface. What's special here is that they have fields called left expression and right expression. This is because these classes are expressions that return the sum or the difference of both values. Each of these fields, being an expression, can be a single number or an expression adding or subtracting multiple numbers. The values for these fields are filled by the constructors of these classes. The interpret method is a method that adds or subtracts the results returned by the interpret of both expressions. Whether numbers come on the left and right, or complex expressions come, one number that has all the results calculated is returned as a result. Finally, here is the client code. First, create a representation of numbers like this. Then, create a representation of adding two numbers like this. On either side of this expression, there are simple numbers. And then, create an expression to subtract 3 from the result of adding these two. In this expression, there's another expression on the left. The result of interpreting the expression, subtracting 3 from the result of interpreting the expression, adding 5 and 2 is 4, as you can see here. So we've been able to see how such expressions that return specific values are implemented and used as classes through the interpreter pattern. This time we're going to make a program that processes this SQL query statement. This example will include the process of parsing this query given as a string. Although we will implement only a tiny part of the program's capabilities, it will involve a larger amount of code than the examples we've been dealing with so far. First is the context class that simulates a database. In reality, we would use a database table like the one on the right, but here we've implemented it using maps and lists. In this way, we enter data from two people, consisting of ID numbers, names and ages, into a table called users. As a result, a list of maps, like the table on the right, will be in a map called tables. And these methods are ones that take a specific table from tables or insert a new table. Up next, we will talk about the interface of expressions. This example deals with rows consisting of columns. For this reason, we use a list of maps as the return type of data. Now, let's look at the two classes using this interface. First, let's consider the where expression, which is a conditional statement, on the right side. For this query, it selects the rows of users who are older than 27. Here is the class of this conditional expression. It has column, operator, value, and table name as fields. In the query just seen, the values will be age, greater than, 27, and users respectively. It receives these values from the constructor like this. On the right side, it has a method that returns a boolean indicating whether the given row meets the given condition. For the current query, it would return true if a value greater than 27 is contained in the age column of the given row. And this interpret method returns the rows that satisfy the condition in the given context. In this way, create a list called result testing each row of the given table with the method on the right and storing only those rows that return true in the result list. And finally, it returns that result list. Now, let's look at the class of this select statements expression. As you can see, this query is an expression that includes the where clause we just looked at. Here is the class of the select expression. It takes the table name to be queried, the columns to be fetched, and the where clause to be used as fields. It takes these from the constructor. In the interpret method, we first take the table to be queried from the given context. And here too, we make a list of rows to be returned. Now select the appropriate rows for the query from the picked table and put them in the result list. If there is no condition statement or the result of testing each row with a where statement is not an empty list, then the row is added to the result list. Finally, we return this list as the result of the query. The following class passes a query given in text into expression classes. First, it splits the query string based on the spaces. The parser in this example only handles select statements. Columns to be selected are made into a list separated by commas like this. The name of the table to be queried is also extracted in this way. And if there is a where clause, it is split into elements to create an instance of the where expression. These extracted elements are used as arguments to create an instance of a select statement. Here is the client's code finally. First, create an instance of the context that acts as a database. Now I will run this query statement without a conditional statement. It fetches all rows and columns. Populate an instance of the expression by parsing this query string. When you interpret this expression, the rows are returned in a list like this. When you print these, all user data stored in the database is displayed like this. Now I will run the next query. A conditional statement is attached, saying that only users whose age value is greater than 27 are fetched like this. This part is created as an instance of the where expression and used in the select expression, so you can see the filtered result like this. Like so, the interpreter pattern defines the grammar of a certain language and builds an interpreter that matches it. This allows us to flexibly interpret and process complex grammar or commands. Next time, we will learn about the publisher-subscriber pattern. The 23rd pattern is the publisher-subscriber pattern. This pattern is similar to the observer pattern we've covered before. The observer pattern had the form of a single subject, sending messages that multiple observers would receive. The publisher-subscriber pattern that we're going to learn this time looks like this. The subject is now called a publisher, and the observers are subscribers. But the significant change is that a broker has been added between the two. The publisher sends a message to the broker, and then the broker delivers it to the subscribers. There are two advantages to this method of adding a broker in the middle. One is that it completely separates the publisher from the subscribers, reducing their dependencies on each other, and the other is that it's more suitable for asynchronous task processing. Let's look at the code. This class is a message class that will be passed between a publisher and a subscriber. It's not an essential element of this pattern. As you can see, it has these fields called content and topic. The rest are constructors that get their values, along with the setters and getters for them. These codes are the core elements of the pattern. First, there are interfaces for the publisher and the subscriber. Each has a method for publishing a message and a method for receiving and updating the state. They communicate with each other, with the broker on the right in between. The broker has a list of subscribers for each topic of message. This subscription method gets subscribers added to the list corresponding to a given topic. For example, when registering a new subscriber to the sports topic, it finds the list with sports as the key in the map and puts it there. If there's no list for that topic, a new one is created and then the subscriber is added to it. The publish method, which sends messages to subscribers, is called from a class that implements the publisher interface. First, it retrieves from the map a list of subscribers who subscribe to the given message's topic. And then, it sends the message via the update method of the registered subscribers on the list. Next are the concrete classes implementing the publisher and subscriber respectively. As you can see, the publisher has an instance of the broker as a field. It structures in a way that the publisher knows the broker and the broker knows the subscribers. You can guess easily that the publisher's publish method calls the broker's publish method. For our subscribers, we have this name field here to differentiate instances. An update method is implemented to print out messages called from the broker. Finally, here's our client code. We first create an instance of the broker and then also create an instance of the publisher that takes this broker as a recipient. Now let's create instances of 2 subscribers and add them to the broker's subscriber list. As you can see, it enables subscription by topics. Subscriber 1 is subscribing only to sports, and subscriber 2 is subscribing to both sports and weather. Now, when we publish news about sports, both subscriber 1 and 2 receive it, and in the case of weather-related news, only subscriber 2 receives it like this. In this pattern, it's because the publisher and the subscribers are fully separated like this that we can modify or extend the system components more flexibly. Now, let's take a look at an example of asynchronous work. This pattern allows the publisher to be separated from time-consuming asynchronous tasks by delegating the job of sending messages to the subscribers to the broker. First, we have the class that corresponds to the publisher. This class, called Email Good Delivery Service, will take the role of the broker. In this example, we don't have a separate class for the event being transmitted, and the type of event is a field value that the publisher has. In the constructor, it fetches the values of the broker and the event type and saves them in the fields. When the campaign start method is called, it calls the broker's send email method with the event type as the argument. Here is the subscriber interface and its implemented class. On this part, the method of reading emails corresponds to a function that receives messages from a broker. The significant part is that there is a place where it consumes 5 seconds. If the broker handles this part synchronously, each subscriber will have to wait for 5 seconds until the previous subscriber finishes reading their email. As the number of subscribers increases, it will take a long time for all subscribers to read their emails. Now let's take a look at the broker's code. The process of adding a subscriber is the same as the first example. The noteworthy part is this task of sending emails is implemented asynchronously like this. In other words, threads other than the main thread are created to handle multiple tasks simultaneously. For those who do not use Java, you just need to know that these codes are one of the ways to perform asynchronous tasks in Java. This is the code that delivers events to the subscribers registered in the list asynchronously. Let's take a look at the client code now. First, we create an instance of the broker, and then we create an instance of a publisher that uses this broker. Now we're going to create subscribers 1 and 2 and register them with the broker, then let the publisher publish the first event. Pay attention to this sequence. Then we create subscriber 3 and register it with the broker, followed by triggering the next event. This part of the code deals with concluding the asynchronous tasks. So, if you're not a Java user, feel free to skip this. If you run this code, you will first see the output as shown on the right. As you can see, the message printed when the second event is triggered is above the message printed when subscribers receive the first event. This is something that shows the processes are carried out asynchronously. The order below tends to change every time you run, because the order in which threads process their work is not fixed. And, as you can see, the results of the events sent to the subscribers after 5 seconds are displayed simultaneously. This happens because the broker is responsible for transmitting the event to the subscribers, so the publisher can focus solely on event publishing without having to concern about whether the task is processed asynchronously or not. As such, the publisher-subscriber pattern provides efficient asynchronous communication and scalability in complex distributed systems, maintaining loose coupling amongst components and enabling the implementation of flexible and scalable event-driven architectures. Next time we will look into the Iterator pattern. The 24th pattern is the Iterator pattern. Most modern programming languages provide libraries that perform the role of an iterator, or have a function equivalent to it in the language's own syntax.
So, does that mean we don't really need to code and implement the Iterator pattern ourselves in real business?
Yes, but by learning this pattern, we can examine the principle on which the iterator is implemented and get hints on how to apply and utilize it when a new type of collection is required. Let's start off by talking about this iterator. In programming, there are various data structures that can hold multiple data. Various collections, such as arrays, maps, linked lists, and stacks, manage multiple data in their unique ways. Because they have different structures and principles, the way they move from the previous element to the next element is different. Just like buses, trains, and trams have different ways of getting to the next stop or station. The iterator's job is to navigate through the elements one by one in the corresponding collection. Metaphorically speaking, these iterators act as the drivers of each bus, train, and tram. Typically, they have the ability to move to the next element and check if there is a next element. These might look like just two small features, but many functions related to the collection are written based on these two. By being able to give these drivers and engineers common commands like go to the next stop or tell me if you can go further, you can implement various advanced features that can be commonly applied to various collections. Various features such as collection-specific traversal syntax, various functional features, and generators in each language are based on iterators. Let's look at the first example. In this example, we will understand the principle by directly implementing a simple list data type and its iterator. First is MyIterator interface. Like this, there is a hasNext method which checks if the next element exists, and the next method which returns the current element and then moves to the next one. The implementation will vary depending on which collection to make into an iterator. Next is the interface of the collection that we will implement ourselves. It declares a method that returns a dedicated iterator for the collection, that is, the driver who drives this collection. On the right, we have the MyList class where it's applied. Although it's called a list, as you can see from this part, its functions are virtually the same as Java's basic arrays. What's important is that it returns an iterator of the MyIterator data type. It's an instance of the class we're going to examine with the following code. This is a MyListIterator class that applies the MyIterator interface. First, it holds an instance of MyList, which it will operate on as its argument. And since the index starts operating from the 0th position, it is assigned O in the constructor. The two methods below are concretized to fit the MyList class. In case of hasNext, it returns whether the index is less than the return value of the list size method, and the method that moves to the next element returns the current index value and then increases the index value by 1. Finally, we have the client code. First, we create an instance of MyList. It's created with a set size, much like an array. Next, we use the add method like this to insert data. Now we bring over the driver in this list, the iterator. With a while statement and the methods of the iterators, you can print out all the elements in the list like this. Regardless of what kind of collection you create, code that uses iterators will stay the same. Hence, by utilizing the common interface of iterators, we can create a variety of useful functions related to collections. Next, we'll take a look at examples of creating iterators for different purposes. Like this, we've covered examples of creating a file system using composite patterns. A composite can also be a collection, so you can create an iterator to apply. In a composite, there are ways to traverse, preferring either depth or breadth. Iterators can be made for each of these. In such file systems, when exploring all sub-elements from the root folder, both will reach this user folder in the same process. But depending on whether you explore in depth or in breadth, it will determine which file you view first. Now let's look at the codes. This is the file system interface and the file and directory classes that apply it. As we've seen in the composite pattern example, I don't think this code needs to be explained again. Now here's the iterator interface for traversing this file system. Like other iterator interfaces, the hasNext method and the next method are declared. I'm going to implement these iterator applied classes to first explore one vertically and the other horizontally. First, it's an iterator that traverses in depth first order. This iterator utilizes a stack as a collection to hold the internal elements. This part is what makes it different from the next iterator. From the constructor, it brings in the instance of a directory and adds this to the stack. Therefore, at first, there would only be the top level directory that this iterator handles in the stack. The hasNext method returns the status whether the stack is not empty. The next method is the complex part. In the end, it returns the last element in the stack. Before that, if the element where the current iterator is positioned is a directory, it will add the elements inside of it to the stack in reverse order. You may take your time to analyze this part after you've watched the whole video. Next, we have the breadth first iterator. As you can see, here we use a queue, in contrast to the previous iterator. And in the next method, when the element is a directory, the internal elements are added to the queue in their original order. This difference causes the search order of the iterator to change. Lastly, although not mandatory, this is the class that links them with the elements of the file system. First, it receives a directory to be used as the top-level folder through the constructor and saves it as a field. And there are methods that return two versions of iterators starting from the directory. Now let's take a look at the client code. First, create files and directories and arrange them as shown on the right. You've seen this part in the Composite Pattern example, so I don't need to explain it. Now, register the root folder as the top folder of the file system. Whichever way you navigate, the sequence up to this user folder will be the same. If proceeding with the depth-first navigation first, according to the iterator implemented, you will visit the child elements before the sibling elements. As such, file 1 is printed before file 3. On the other hand, in breadth-first navigation, you will consult the sibling elements before the child elements. Thus, you can see file 3 is printed first. Understanding how the difference between stacks and queues results in such an outcome is not an important part here, so you can slowly analyze this later. The point to remember in this example is that you can create an iterator to traverse the collection in a specific way according to your needs. Next time will finally be the last pattern. We will explore the Specification Pattern as the last pattern. At last, we've reached the final pattern. Since it's the last, I've prepared a pattern that is relatively easy to understand, not too difficult. We'll conclude the lesson by learning about the Specification Pattern. This pattern is useful when checking whether the attributes or behaviors of an object meet certain conditions. You can create reusable objects with multiple conditions and combine them to generate various new specifications. Let's start by looking at the first example. It's a simple program that checks whether a given integer meets certain criteria. First, we have the interface of the specifications. The important method here is the one returning whether the parameter meets certain conditions. This interface will be implemented in each class it applies to. We'll take a look at this AND method in a moment. On the right are classes implementing this interface. The method implemented in this class returns whether a given integer is even. In other words, it is a class that specifies whether it's even. The next class, like this one, receives a minimum value and a maximum value from the constructor and holds them in its fields. It's overridden a method to return whether the given number doesn't exceed these ranges. So, this is a class that represents the specification of a range. Now, let's get back to this AND method of the interface. In Java, methods declared as default can be implemented like this in interfaces. This method receives an instance of another specification as a parameter and returns a new instance of a specification. The evaluation method of this instance returns whether both the specification that executed this method and the specification that came in as a parameter return true for the given integer. Even if you don't understand this part, let's move on to the next code for now. This is the client code. First, let's make instances of even number specification and range specification of 10 to 20 like this. I'm going to test whether 24 satisfies this specification. First, you can see that the even number specification is satisfied like this. In the case of the range specification, you can see that it does not meet like this. Now, let's look at the segment with AND usage. We've already seen that when one specification takes another as a parameter and performs the AND method, a new specification is returned. So, a specification where an even number specification and a range specification are combined by AND operation has been created this way. When you test a number with this specification, it will return whether the number is even and between 10 and 20.
If I can do AND, does that mean I can do OR and other things too?
Of course. We will look at programs that use a variety of combinations and modifications. Let's move on to the second example. It's not part of the pattern, but here's the product class, which will be the evaluation subject of the specifications. It has fields like name, category, price, stock, and related constructors and getters. Here are the codes for the specifications. This specification interface simply contains a method to evaluate the given parameters. The remaining three classes apply these specifications. Specification to check if the product belongs to a certain category, specification to verify if the product's price is below a standard price, and a specification to check if there is stock left for the product. Next are the specifications for combining or modifying them. And, or, and not operations are made into specifications. If you separate them into different classes like this, you can add other operations like XOR more flexibly in the future. Both AND and OR specifications take two other specifications as parameters and return a new specification. Each returns the AND or OR operation as an evaluation result of the two specifications. NOT takes one specification as a parameter and returns the opposite value of its evaluation result. This is a class separated to reduce the length of the main class, though it's not a necessity. We have a filter method first. It takes a list and a specification as parameters and returns a new list containing only those items in the list that return true in the specification. Below is a method that prints each product in the list received as a parameter. Finally, here is the client code. First, we generate instances of the products like this and add them to the list. Below are instances of specifications regarding the category, whether there is stock left, and the price. Then we form specifications that combine these with AND or OR, or reverse them with NOT. If you filter up products that are in the electronic category and still have stock left, you would get a result like on the right. Below that is the output of products that are either electronic or still left in stock. Finally, if you filter out products that are higher than the standard price, you get high-priced products as a result. You can establish the specifications of other logical operations like XOR, or even complex specifications that combine 3 or more, using this. With that, we have covered all 25 patterns prepared for this lecture. Through this, you should understand how object-oriented languages and their capabilities can be utilized in practice. Moreover, how to write efficient, stable, and expandable programs. I hope that you apply the patterns you learned in this lecture suitably to your future projects. That way, you'll be able to write more robust and flexible code. I will see you in the next lecture with even more useful and valuable content. Thank you for joining me.